A planet turns in quiet, a young world just past its violent birth. Stone that once glowed like a sea of fire now cools into surfaces that can hold memory, though nothing yet breathes to remember them. The crust stiffens, still thin, still cracked by the lingering heat within, a shell that clicks and sighs as convection heaves beneath it. Above, an atmosphere without mercy presses down, a heavy cloak of steam, carbon dioxide, nitrogen, and sulfur vapors. No bird cuts these winds, no leaf trades gases with this sky. The light from the infant sun falls through a veil of haze, and where the air is clearer, it arrives unfiltered, a glare that bites. There is no ozone to soften ultraviolet blades, no oxygen to taste on an absent tongue. Nothing weighs the moment except rock, gas, and the tensions held between them. Seas swell from vapor, first as endless rain, then as basins that gather into wandering oceans, hot and mineral-rich. The waves are not yet familiar, their chemistry a rough draft, brined with iron and magnesium, flavored by chloride and sulfide, streaked by volcanic ash. Their colors shift with depth and dissolved metals, green where ferrous ions are thick, coppery where suspended dust scatters the light, pewter where sulfur clouds cast a pall. They throw themselves against newborn shores that crumble easily, shores built from lavas that once bubbled, then froze, then broke. Basalts dominate, dark and glassy, ribboned with vesicles where trapped gases fled. In the lowlands, impact scars fill with water and chemistry. In the highlands, gases hiss from fractures, and new land heaves out of vented heat. The moon stands nearer in this sky, a large coin with ragged edges, tugging at the oceans with a gravity that feels personal. Tides run strong, dragging inland to improbable distances, then retreating with a speed that bears rocks and steaming pools. The planet spins quickly, its day short, the stars wheel fast, and shadows never sit for long. Between midday glare and midnight chill, the temperature swings hard. The winds carry grit and acid, they smell of lightning and brimstone, and they hurl salt spray across a coast, still learning its name. No scent is welcomed by a living thing, yet even without witness the air has character, a chemistry that rehearses future possibilities. Volcanoes speak the loudest. They spit fountains that fall as black rain. They build temporary mountains that slump as soon as they grow. They cough sulfur and chlorine into clouds that curdle the sky. They release methane in trickles and carbon monoxide in pulses. They send water vapor in torrents. In their calderas, boiling lakes churn with dissolved metals. Their margins rime with crystals that evaporate into delicate geometries. Far offshore, submarine eruptions pile pillows of glass, crack them, and heat the seawater that rushes in. Thermal plumes rise like ghostly columns, rich in hydrogen, rich in minerals, offering gradients of temperature that would one day mean metabolism, though now they mean only physics and flow. Lightning fractures the clouds with sudden instruction. Bolts carve momentary threads of plasma through the wet air, knit nitrogen into new forms, and leave behind a smell of sharp change. Storms go on for days, driven by the fever of a cooling crust and the deep energy of the mantle. Hailstones are not yet made of ice alone. They carry ash and acids, they pock the soft surfaces along the shores, they melt in rivulets that carry metals toward the sea. Rivers braid across plains that had no names, their channels shifting with each flood, their deltas collapsing, rebuilding, collapsing again. Each drop that falls carries heat away from the planet. Each plume that rises carries heat upward, and the balance of those motions sets the pace of the world. The stars are older than this place, but they watch without judgment. Occasionally one seems to fall, a pebble of space rock that flares and hisses, sometimes a boulder that survives the plunge. Bodies strike often in these early days. Some deliver water bound in minerals and ice. Some deliver carbon compounds forged between the planets, or in the cold, dark beyond. Simple molecules that can still surprise when warmed and wetted. Others deliver only force, a clean blast that resets a landscape, boils a sea surface, stirs the air into global winter, then seeds to a greenhouse that overshoots. The crust bears the bruises, then self-heals, then bruises again, in a cycle that teaches the planet endurance. In the quiet after a storm, the seas steam like animals that breathe, Bubbles rise from fissures and pop, leaving films that cling to the water, delicate skins that trap a moment of order before they rupture. Minerals flake from rocks and drift as silts. Clays form in sheltered inlets, their platelets thin and welcoming. On a flat stone warmed by the pale afternoon, a thin sheet of water pulls back and leaves behind a stain of salts that will be taken by the next wave, then left again, then taken again, in repetitions that carve rhythm into chemistry. There is no meaning here except pattern, yet pattern is a kind of prelude. Under the crust, heat carries the planet's old violence forward. Mantle currents slow, but they do not stop. They loft plumes that thin the lithosphere and feed long fissured ridges. Along those ridges, magma quells its impatience by building new floor, pushing older rocks sideways, forcing them to wrinkle, break, and dive where they find a weakness. The geometry is not fixed, but the intent is clear. Energy seeks release, mass seeks rest. Planetary architecture appears from a scaffold of stress. In deep pockets, crystals grow from cooling melts, tight lattices that speak the language of order. Zircon, stubborn and compact, captures fragments of time in its hearts of lead and uranium, little clocks waiting for readers who do not exist. The clockwork tick is inaudible. Still, it sets a cadence that the planet will keep. At the poles, if poles can yet be drawn, ice experiments with permanence. The air is thick with greenhouse gases, the sun is faint by later standards, and the balance between them swings. There may be intervals when the snowline descends, when seasonal shells of ice frame the early oceans, when albedo fights greenhouse to a standstill. Then volcanoes surge, or impact winters fade, or the ocean breathes out the heat it had hidden, and the grip of cold releases. The world learns its ranges, from hot basins bordered by scorched lavas, to high plateaus chilled under muted light, to temperate shelves wrinkled by tides that pound like a heartbeat. Sound carries in every medium. Inside the planet, tremors speak in long voices, drumbeats of fault and fold. On the surface, waves knock at stone with a percussion that never tires. In the sky, thunder rolls beneath a ceiling of vapor, the echoes trapped and layered until they become a constant murmur. If ears had been possible, they would have heard a world that hums. If eyes had been possible, they would have seen a palette of metals and salts, of smokes and waters, with no green to soften the edges. Yet there is softness here, in the curved shapes of dunes made from cinder, in the slow sway of vapors rising from a warm pool, in the gentle slur of a shoreline that rearranges itself by millimeters each hour. Magnetism stitches the space around the planet. Deep within, a core of iron and nickel swirls and solidifies in layers, and electric currents organize into a shield. Charged particles from the sun notice. They veer, they spiral along invisible lines, they paint the high atmosphere with lights that no eye can see, and they spare the lower skies from harsh radiations that would strip and sterilize with more efficiency than they already do. The shield is imperfect, variable, youthful like the world itself. Still, it matters. It allows a future tension between destruction and protection, a stable arena where fragile things might someday test their balance. Time moves without witness. With each turn, the chemical inventory adjusts. Dissolved carbon equilibrates with rocks. Carbonates settle from hot shallows and lock away gas that once ruled the air. Silicates weather to clays that sip cations, returning them to the sea in measured drips. Sulfur cycles between vapor and crust. Acid rains etch lavas. Vents repay the debt with fresh injections. In deep waters, minerals precipitate as chimneys that grow and break, a forest of stone that gets replanted by heat. The atmosphere thins a little, then thickens, a restless lung without a body. The sea cools, then warms, then cools, never bored. No voice calls it beautiful, or harsh, or home. Yet in the interplay of temperature and pressure, in the restless flow of water across rock, in the flashes of energy from above, and the gradients of energy from below, there is a stubborn invitation. Disorder tampers with order, then loses ground, then regroups. Structures form and fall apart, then form again with slightly more bias. Sheets of ice form patterns no artist drew. Crystal fans net minerals in abandoned pools. Bubbles scaffold brief compartments that carry different chemistry inside than out. Everything is temporary, yet nothing is meaningless, because meaning is simply what persists long enough to become noticeable, and persistence is slowly gaining leverage. A cloud bank parts and lets a clean shaft of light strike a steaming shore. The beam reflects off a wet basalt pillow, travels through air flavored by salt and ash, splits on droplets and makes a muted, colorless rainbow that fades as quickly as it appears. In that single gesture is the world as it stands. Energy arrives, matter responds, structures flare, then collapse, then leave a trace in the next thing that happens. The planet is a stage that builds itself while the play begins. Silence is not the absence of story here. Silence is the script written in heat, in mineral, in vapor, waiting for a voice that can read. Fire writes the first grammar of the planet. Pebbles of dust gather inside a collapsing nebula, drawn by gravity and glued by heat, until they become stones, then boulders, then sprawling clumps that collide with a violence both creative and precise. Each impact melts surfaces into glass and welds fragments into larger bodies called planetesimals. Radioactive aluminum and iron inside those bodies shed heat like hidden furnaces, raising temperatures past the point where rock remembers its shape. Metal separates from silicate. Droplets of iron sink like rain inside molten interiors, the building blocks that will become a world learns stratification before they learn stability. The collisions intensify as orbits cross and resonate. Gravitation does not care for symmetry. Some impacts shear away half a body, some only bruise. The lucky outcomes grow mass, the unlucky become gravel. Over millions of years, a dominant embryo emerges on a track between a young sun and a ring of asteroids. It sweeps its lane with a hunger measured in craters. Every strike releases a storm of energy, plumes that arc into space, curtains of melt that fall back as glassy hail. Shock waves fracture the crust of the temporary surface, then erase it as a new layer of melt floods across. The embryo becomes a planet not in a single birth, but in 1,000 interruptions. Differentiation follows inevitably from heat. Metal seeks the center, forming a core that pours downward through lighter silicates as a glittering rain. The core grows into a sphere of iron and nickel with traces of sulfur and carbon, a weight at the heart that will one day power a magnetic shield. Above it, the mantle churns like a slow storm, crystal networks assembling and dissolving as pressure and temperature trade influence. The remnants of short-lived isotopes keep the pot boiling. Long-lived heat makers in uranium, thorium, and potassium add endurance to the burn. Convection sets patterns that become the planet's first architecture, even while the surface remains an ocean of rock. A collision larger than the rest interrupts the sequence and sets the tilt of the planet's life so far. A body about the size of Mars arrives on a near miss that is not a miss at all. The striking mass tears away a volume of mantle, mixes it with the projectile's own silicates, and ejects a ring of incandescent debris. In that ring, molten droplets find each other, tides sculpt clumps into spheres, and a single companion takes shape. The new moon orbits close enough to appear colossal in any sky that might have existed. Its gravity stirs the magma ocean into tides of rock. The exchange of angular momentum slows the planet's spin and pulls the moon outward with each passing cycle. Obliquity is set. Seasons become inevitable, and the length of day begins the long drift from frantic to familiar. The magma ocean cools from the top. A skin thickens, then sinks where it grows heavy with crystals. This overturn repeats, turning a surface into a conveyor that delivers heat to the air. Massive plumes wring gas from molten silicate. Volatile elements gathered during accretion escape fireworks of steam, carbon dioxide, nitrogen, and sulfur-bearing molecules that veil the planet in a dense atmosphere. The pressure is crushing, the greenhouse effect extreme, the rain, a scalding cascade that returns dissolved minerals to basins yet too hot to hold gentle water. The sky glows with scattered light through volcanic haze, and the horizon shimmers where convection blurs boundary lines between land and air. During cooling, crystals grow in the melt, like ideas becoming structure. Olivine and pyroxene settle first, forming cumulate layers that insulate and redirect flow. Feldspar segregates, making rafts of buoyant plagioclase that drift like icebergs in rock. In the deep mantle, High-pressure phases fold into unfamiliar symmetries, packed dense enough to guide sound at strange speeds. Pockets of trapped gases form, then burst, venting sills and dikes that cut upward like veins. Each eruption draws a map for a moment, then redraws it with the next surge. In places where the surface solidifies, impacts return to carve and reset, reminding the young crust that permanence is still a future talent. Metal does not travel alone. Siderophile elements that love iron vanish into the core, leaving the mantle oddly depleted. Later, a rain of small asteroids and comets delivers a thin garnish of these precious elements back to the surface, a late veneer that adjusts the chemical ledger. Water tags along in hydrated minerals and icy grains, adding mass to the already generous steam that the interior has exhaled. Carbon compounds arrive, embedded in carbonaceous bodies that outgassed in the darkness beyond the frost line. Each delivery changes the recipe of the atmosphere and the oceans that will condense from it, adding flexibility to future chemistry. Magnetism flickers into being as the core convects. Liquid iron moves in spirals and sheets, generating a dynamo that threads space with invisible lines. Charged particles from the sun surf those lines, some trapped, some redirected, some digging into the upper atmosphere with energy that breaks molecules and stitches them into new forms. The field waxes and wanes with the vigor of the core, its symmetry imperfect, its polarity prone to reversal once the system matures. Even in youth, it offers partial shelter against the relentless wind of particles racing outward from a star not yet settled into its own quiet rhythm. Angular momentum defines comfort. The newly formed moon stirs tides in the magma, and in any early seas that gather on cooling rock. Those tides pump heat in and out of fractures, flexing the crust and leaking energy that would otherwise be trapped. The planet rotates quickly, turning shadows into strobe and distributing heat before it can pile up into extremes. As time goes on, lengthening days slip the gear teeth of weather and ocean, allowing slower patterns to assert themselves. What begins as raw speed becomes the measure that future winds and waves will keep. Impact basins become laboratories for textures. A basin excavated by a giant strike fills with pools of melt that crystallize at different rates. Rapid cooling traps glassy sheets. Slower cooling breeds interlocking crystals. The shatter cones of fractured rock record shock as geometry, their surfaces etched with fan-like ribs that point back toward the unimaginable pressure of the event. Ejector blankets spread outward in layered carpets, sorting by size and angle, only to be overturned by the next visitor from space. A palimpsest forms, a layered record of violence that future readers will decipher in zircon cores and isotope ratios. Degassing thickens the air further. Steam condenses whenever the surface drops below the boiling point, but volcanism writes new clouds as fast as rain can erase them. Carbon dioxide accumulates because there is no plant life to bind it into tissue, no limestone factories driven by biology to hide it in stone. Nitrogen becomes the quiet majority, a background gas that refuses chemistry except under the harshest stimuli. Methane pulses in from ultramafic rocks as serpentinization proceeds where water meets fresh mantle. Hydrogen leaks from vents and escapes into space if it finds a path fast enough. Chemistry tests its moves with no feedback from living metabolism, and the air becomes a mirror of rock and heat. Inside the mantle, currents organize into patterns that resemble continents of motion rather than land. Upwelling plumes punch at the crust and form provinces of flood basalt when they succeed. Downwelling slabs return cooler material to depth, though the mechanics of subduction will sharpen only as the planet stiffens. Thermal stress carves a lacework of fractures across the cooling surface. Those cracks admit water once it can persist, and water weakens rock, and weakness invites motion. Tectonics glimmers as a possibility, a planetary habit not yet matured, but already rehearsed in slow, grinding gestures. Evidence for these earliest chapters will one day be read in stones far from their birthplace. Ancient zircon crystals store uranium that slowly turns to lead at a tempo set by physics. The ratios point backward toward formation ages and cooling histories measured in numbers with many zeros. Meteorites deliver snapshots of time capsules that never grew large enough to become worlds. and in their inclusions lie traces of the radioactive heat that cooked the building blocks. Pieces of the moon carry complementary signatures, oxygen isotopes that rhyme with Earth's own story, suggesting a shared origin in that catastrophic embrace. Every choice made by gravity and heat in this period sets boundary conditions for everything that follows. The size of the core regulates the dynamo. The export of gases defines the pressure and composition of air and ocean. The speed of rotation frames climate, currents, and tides. Obliquity draws seasons on the calendar of orbit. The tilt is neither too small nor too wild, the spin neither too rapid nor too languid, the air neither absent nor suffocating beyond repair. Contingency feels like design only because survivors read it. In truth, the early system explores parameter space with a blind patience, and the outcome rests on thresholds crossed and thresholds avoided. As rock cools toward rigidity and the rain of fire slackens, the planet gathers itself into a quieter stance. Heat still seeps from within, but not in sheets of incandescent flood. Air still thickens and thins with volcanic moods, but not in the choking surges that once dominated. The moon drifts outward handspan by handspan of cosmic distance, stretching tides into rhythms that will one day pace shorelines and stir basins with oxygen. The violence of assembly fades into the subtlety of maintenance. What remains is a world with layered density, a circulating mantle, a volatile rich surface, and a sky that traps warmth. The furnace that forged it has not gone cold. It has simply banked its fires into a long endurance, ready to feed water, weather, and the first experiments of chemistry that will someday learn to copy themselves. Rain begins like an instruction that cannot be ignored. Vapor condenses into beads, beads gather into curtains, and curtains become oceans that claim the low places with a patience measured in centuries. Clouds build themselves from steam lofted by warm rock and cooled by expanding air, their bellies heavy with droplets that collide until gravity wins. Each fall is a negotiation between buoyancy and weight, between ambient heat and evaporative chill. The result is water that reaches the surface still hot, salt-hungry, and ready to dissolve whatever will surrender. Rivulets coalesce into braided torrents that carve temporary channels across dark volcanic provinces, delivering a worldwide cargo of ions toward basins where salinity is born. Chemistry follows the rain. Carbon dioxide dissolves into the first seas and forms carbonic acid that tugs cations from basalt. Calcium and magnesium slip from crystal lattices to meet carbonate and bicarbonate, a partnership that eventually settles as mineral rain on the seafloor. Sodium lingers in solution, less eager to precipitate, more willing to ride the waves. Chloride arrives from volcanic gases and from minerals that weather into surrender, becoming the partner that will dominate seawater. Iron darkens each inlet as ferrous ions leach from fresh rock and remain soluble in an oxygen-starved world. The color of the water shifts with mood and solute, green where iron thickens, tea-brown where silicates cloud the shallows, pewter where ash drifts through the column. Temperature imposes a structure of its own. Heat rises from vents and from a crust still shedding its fever. Sunlight, unsoftened by ozone, penetrates to a degree set by haze and aerosols in the air, warming an upper skin more quickly than the depths. A tentative stratification appears, a stably layered sea in quiet stretches, and a churned water column where storms and tides prevail. Surface temperatures ride high by later standards, a realm that can simmer at 50 degrees or more during calm intervals, then cool abruptly under sheets of rain that fall from anvils of towering clouds. Thermal gradients translate into density gradients that guide circulation, drawing deep water into contact with hot rock at mid-ocean ridges and returning it altered, metal-rich and buoyant. Tides become an architect. A nearby moon pulls at entire basins with a strength strong enough to drag walls of water across shelves and up embayments. The rise floods flats that crackle with freshly cooled lava, then the fall strands pools that steam under the open sky. These oscillations create cycles of wetting and drying on scales from kilometers to centimeters. They focus energy on shorelines where waves comb minerals into fines and lay them into thin films. They drive currents that sweep along the base of cliffs and across nascent deltas, selecting grains by size, polishing stones into shingle and leaving terraces that stage the next flood. Hydraulic forces press water through pores of newly formed rock, priming serpentinization and other reactions that generate hydrogen and alter local pH. The sea surface itself becomes a lens, a membrane, a stage for subtle physics. Between air and water lies a microlayer, only molecules thick, enriched in organics delivered by meteorites and volcanoes, in dust blown from distant fields of ash, and in salts concentrated by evaporation. Capillary waves swarm along this skin, their ripples altering reflectivity and mixing. Foam forms where waves break and persists a little longer than expected, stabilized by trace compounds that change surface tension. Sunlight strikes at low angles and glances off as glare, then strikes at high angles and penetrates to scatter from suspended particles. Within this skin, life will one day harvest photons. For now, it modulates energy and chemistry by texture and motion alone. Hydrothermal systems awaken along spreading ridges and in volcanic provinces beneath the sea. Cold water infiltrates cracks and fractures, heats as it descends, dissolves metals and sulfide from hot rock, then rises in shimmering plumes. The fluids mix with ocean water and deposit minerals as chimneys that grow upward like stalagmites built from heat. These vents stitch gradients of temperature, pH, and redox into the water column, gradients that can span meters yet remain surprisingly stable. Their output supplies iron, manganese, and zinc in soluble forms that drift and settle as chemical sediments when conditions relax. The surrounding terrain becomes an amphitheater of contrasts. Scorching fluids beside near-freezing abyssal water, acidic niches beside alkaline pockets, silicate walls beside carbonate platforms. Weather continues to shape the plan. Storm tracks trace belts, where temperature differences and planetary rotation conspire to spin cyclones out of instability. Convective towers climb high, planed flat at their tops by wind shear. Lightning scrawls branching maps through humid air, forming nitric oxides and other reactive species that wash into the sea with the rain. Hail forms around ash particles, grows layered like tree rings, and falls into open water where it melts and slots a pulse of cold, freshened brine into the upper ocean. Evaporation leaves behind salts on hot flats and makes brines that sink when they return to the sea. Quiet cascades sliding along the bottom, like underwater rivers. Mineral deposition keeps time below the waves. Where water chemistry tips towards saturation, mountains of carbonate ooze can gather in warm, shallow margins, while silica-rich waters leave chert in layers that begin thin and become thicker with patience. Iron dissolved in anoxic seawater precipitates where it meets local oxidants produced by lightning, ultraviolet chemistry, or catalytic mineral surfaces. Particles of iron oxide settle in pulses, draping the seafloor with alternating bands of color that later become stone. Each lamination encodes a day or a season or a volcanic episode. An archive not yet read but already written with exquisite fidelity. Circulation scales from the local to the planetary. Winds push surface waters in gyres that are steered by land if land exists, and by the curvature of the planet regardless. Where currents diverge, deep water wells upward to see the light for the first time in centuries, carrying with it elements that had settled onto the abyssal plain. Where currents converge, water piles into domes that press downwards and spread as boundary flows along protocoasts. Heat moves not simply from equator to pole, but from shallow to deep and back again, a conveyor whose speed is set by salinity, temperature, and the geometry of basins that are themselves evolving through volcanism and crustal motion. Gases find balance with the new ocean. Carbon dioxide dissolves and returns to the atmosphere in a dance mediated by temperature and alkalinity. Warmer water exhales, cooler water inhales. Nitrogen hardly notices the sea at all, preferring to remain in air unless pressures or chemical tricks force it into solution. Methane bubbles from ultramafic bedrock, where water heals to serpentine and magnetite, ascending in plumes that burst gently at the surface and under certain conditions freeze into clathrates within sediments. Hydrogen rises from the same factories and escapes to space if it can outrun gravity. Oxygen is little more than a reactive rumour generated in small amounts by non-biological photochemistry. swiftly captured by iron and sulfur, waiting eagerly below. Drying and flooding write scripts in the margins. Tidal flats and splash zones concentrate solutes as sunlight and wind draw water upward into vapor. Salts crust into polygonal tiles that trap thin films in their cracks. Clay minerals curl and uncurl, exposing new surfaces that bind and release molecules with each pulse of moisture. Basaltic glass hydrates and becomes palagonite, changing the catalytic landscape at the shoreline. Pools perched above the high tide line heat far beyond the surrounding ocean under the noonday sun, then cool at night under clear skies, cycling through temperatures that prompt reactions otherwise sluggish in bulk seawater. Each microenvironment revises the inventory of the nearby sea as its contents spill or leak or are torn free by the next surge. The newborn ocean is loud. Wave trains roll in unopposed by reefs or vegetation, their fetch immense, their period long. When they meet, interference patterns sketch diamonds of calm that leap and vanish as if flickered by thought. Booms from collapsing lava deltas shake the shallows. Hisses from pillow lavas whisper, where water meets incandescent melt along the unbroken ridgelines of mid-ocean arcs. The clatter of moving cobbles under surf forms a drumline. If hearing had been available, the line between weather and geology would be difficult to draw, the two merged into a single long voice. Light is both sculptor and hammer. Ultraviolet turns spray into reactive films and splits water vapor in the upper atmosphere, freeing hydrogen to bleed into space and leaving oxygen to be seized by rocks and metals. Visible light warms what it touches and paints the seascape in metallic greens and blues that shift with clouds. Infrared tries to leave but meets greenhouse gases that escort it back toward the surface, a loop that slows cooling and keeps liquid water possible under a star gentler than it will become. At night, the sky is a black vault, the moon a bright stern presence that pulls the ocean into long ovals and sets a cadence that the basins keep without fail. Time teaches the ocean discipline. Salinity stabilizes as the ledger of inputs from rivers and volcanoes balances against the account of minerals locked into sediments. The pH hovers where carbonates can exist, yet not suffocate the sea and stone. The crust thickens, altering the depth of basins and the shape of continental shelves, reworking currents in the process. Hydrothermal systems mature, their chimneys collapsing and rebuilding as if breathing. Storm seasons find tracks along thermal contrasts and return along similar lanes each cycle. What began as deluge and cauldron becomes a set of habits, and those habits create predictability, and predictability allows complexity to take root. On a windless morning, a bay holds a mirror so perfect that mountains of cooling lava and stacked pillows of glass reflect as inverted worlds. A line of foam traces the quiet impact of small swells rolling in from a distant storm. In the shallows, a sheet of water glides up a basalt step, thins to a silver skin, and retreats, leaving behind a map of evaporated salts fine as frost. The air tastes of chloride and wet stone. Far offshore, a column of shimmering water rises over a vent and bends in the current like a banner. Everything moves, and nothing hurries. The sea is not a passenger. It is an engine that has finally caught, running on gravity, heat, and sky, steady enough to last, and generous enough to host futures that remain unwritten. Air gathers from stone and flame, an atmosphere built by vents, impacts, and the slow exhalation of a hot crust. Its pressure presses like a heavy hand. Its taste would be sour and metallic, its scent a blend of sulfur fog and wet mineral. Carbon dioxide fills most of the volume, nitrogen holds the background, water vapor crowds the gaps whenever the surface steams. Traces of sulfur dioxide and hydrogen sulfide wander in shifting plumes. Methane slips in where ultramafic rock meets water, a local whisper that grows loud after eruptions. Oxygen barely appears, except as a transient spark born in sunlight, and whenever it does, it is seized immediately by iron and sulfur that wait with open bonds. Light enters a sky thick with particles. Droplets of acid form easily, each one a tiny laboratory where gas meets water and writes new chemistry. Volcanic ash lofts into layers that drift for months, their grains scattering shorter wavelengths and giving the canopy a bruised color. In some seasons, a pale copper monotone rules the horizon, In others, a kind of nickel grey spreads from pole to pole. Ozone remains thin, so ultraviolet passes into the lower air and bites at every molecule it can split. The result is an engine of photochemistry that keeps rebuilding the gases, even as volcanoes and oceans rebuild them again by other routes. Clouds dominate the weather. At low levels, thick banks of steam rise where rain has not yet cooled the crust. Higher up, sulfate aerosols nucleate fine veils that spread widely and dim the surface. Towering anvils punch into the upper troposphere in sheets, stacked one atop another like a marching army of storms. Lightning draws jagged calligraphy through these masses and writes nitrogen oxides into the air, a fleeting script erased by rain and recreated with the next flash. Sunlit days are warm, sometimes brutal, but not uniformly bright. Shadows from ash and haze drift across basins like continents that do not touch the ground. Greenhouse physics sets the thermal character. Carbon dioxide traps outgoing infrared within bands that saturate and broaden under pressure. Water vapor amplifies the effect as it cycles rapidly between ocean and cloud. Methane spikes, after local events, add a fast but powerful push. Sulfur dioxide cools the same sky when it converts to sulfate and brightens the aerosol veil. The result is a climate that can tip between sweating calm and reflective chill with changes in outgassing or impact dust. Yet on balance, the blanket wins often enough to keep seas liquid under a star that has not yet reached its mature brightness. Winds form their own geography. Strong equatorial jets run eastward above steaming oceans. Mid-latitude zones breed cyclones whenever temperature differences sharpen along the edges of ash plumes or fresh lava fields. Polar cells organize sluggishly under low sunlight, their inversion layers dense with haze. Dust and ash ride these flows into belts that recur with the planet's rotation, laying down stripes of influence across continents that may be no more than volcanic plateaus for now. When a major eruption sends material into the stratosphere, the world wears a thin ring of sparkling particles along lines of latitude, like a faint crown made of acid ice. Acid rain falls frequently. Carbonic acid forms as soon as carbon dioxide meets droplets, and when sulfur dioxide dissolves, the mixture becomes far stronger. The falls scrape cations from fresh basalt, etch glassy surfaces, and carry metals into streams and bays. On hot flats, puddles shrink into brines, then into crusts of sulfate and chloride that crack like dried paint. When a new storm arrives, the crusts dissolve quickly and feed the sea with a surge of ions. Each rinse changes the balance of the air slightly, because every molecule that becomes a mineral frees the gases that can fill its place. Electrical storms serve as a rolling refinery. Within the dark towers, strong updrafts, separate charge, hail churns, and collects ice skins around ash cores, and collisions grow a thunderhead into a machine for lightning. The bolts reach from cloud to cloud as often as from cloud to ground, forging veins of ionized air tens of kilometers long. In those moments, nitrogen and oxygen jam together into reactive species that rain out as nitrates and nitrites. On plains and shorelines, these compounds soak stones and puddles and quietly alter the acidity and redox potential of surface films. The atmosphere behaves as both canvas and brush, painting the world with products made in thunder. High above, escape sifts the inventory. Hydrogen freed by ultraviolet from water and methane moves fast enough to leak away along the tail of the Maxwellian distribution. Helium lost from radioactive decay follows if it can find an opening. The magnetic field catches some charged particles from the sun and steers them along arcs, but gaps remain where energy punches through. Auroras glow in the thinnest air, where oxygen and nitrogen relax from excitation, their colors invisible to a surface that cannot yet see. Each loss to space demands repayment from volcanoes or the sea, and the exchange never quite ends. Volcanic plumes vary with their sources. Basaltic provinces exhale mostly water vapor and carbon dioxide with streaks of sulfur. Arc volcanism adds chlorine and fluorine in amounts that can etch glass and whiten rock with salts. Ultramafic vents release hydrogen in earnest, where serpentinization eats olivine and stores the heat of reaction. Fumaroles ring calderas with mineral gardens, delicate crystals of green and yellow that crumble into dust at a touch. When rain falls into these features, it emerges as acid strong enough to burn paths down slope, carving channels that smoke as they run. Temperature structures the atmosphere into floors. Near the surface, warmth from the ground keeps air rising in plumes that become clouds. Above those levels, the temperature can level off or climb, where absorption by carbon dioxide and dust outweighs radiative cooling. The stratosphere forms as a region where mixing is slower, its stability borrowed from the temperature inversion. In that quiet realm, sulfate particles can drift without interference and gather into thin sheets that encircle the globe. Radiative transfer inside this layered system becomes a complex conversation of wavelengths, with some lines trapped, some reflected, some free to leave. Gases circulate between air and rock by mineral exchange. Basalts weather to clays under carbonic acid and lock carbon into carbonate minerals that later sink. Sulfur cycles among gas, liquid, and crystalline phases, sometimes as pyrite, sometimes as gypsum, sometimes as lingering acid near the surface. Chlorine rides the wind as hydrochloric vapor from eruptions and returns as a wash of brine along coasts. Fluorine condenses onto ash and falls out locally as white blooms with sharp edges. Each circuit removes certain reactive species from the free atmosphere and binds them in stone, a geochemical ledger that balances over intervals longer than storms and shorter than continents. Visibility changes with every shift in particle size. Fine sulfate makes the sky milky and turns shadows soft. Coarse ash makes the light harsh and drives a glare that bites at unprotected lenses. Water droplets thicken the haze until outlines vanish at a few kilometers. On rare clear days, the color deepens but never reaches the pure blue that oxygen and ozone would later allow. Sunset produces a metallic palette, brass at the horizon, tin above, cold silver near the zenith. Moonlight turns the haze into luminous gauze and stretches halos around bright points. Pressure shapes every breathless inch. With a denser air, sound carries farther and thunder rolls for longer. Waves break differently because air packs more punch against their crests. Raindrops grow large before they fall apart, so downpours arrive as heavy bullets that flatten surfaces into sheets and then into pitted textures where splashes excavate tiny craters. On sea cliffs, the wind shears spray into fog that climbs inland as climbing rivers, moistening rocks that would otherwise remain dry and accelerating the hidden work of weathering. The whole system has a pulse. Gas release rises during basalt floods and during swarms of smaller eruptions. Impacts briefly loft vapor and dust, invite global chills, then hand control back to greenhouse gases as particles fall out. Ocean temperature steers how much carbon dioxide the water can hold, and therefore how much remains in air. When the surface warms, the ocean exhales, and the atmosphere grows thicker with carbon. When the surface cools, the ocean inhales, and the sky relaxes. Feedbacks push and restrain in cycles that can take decades or centuries, slow enough for stone to notice, and fast enough to keep weather restless. On a plain downwind of a volcano, a day begins under a lid of grey. The sun climbs and turns that lid translucent. The wind shifts and the distant plume bends like a black ribbon. Droplets start to gather along the edges of ash grains in the air, then fall as a sour drizzle that etches dark lines into pumice. The smell sharpens, then fades as the shower moves off. Late afternoon brings a widening patch of brightness that slides across the ground like a promise. Night brings heat lightning over the sea, and a low roar from the mountain as gases rise and water falls back. The air never rests, and in its restlessness it carries the planet's heat, its minerals, its sparks, and its memory forward. Rock acquires memory beyond mere cooling when buoyancy begins to sort the planet into layers of purpose. Basalt pours from long fractures and spreads as dark sheets, then sinks where it grows dense with age and cold. In places where heat concentrates, melts rise that are lighter than their parents, rich in silica, pale in color, eager to float. These melts pool into plutons that stall within the crust, crystallize slowly, and form tonalite, trongemite, and granodiorite. Their chemistry grants buoyancy, their texture grants strength, and their collective presence creates rafts that resist submergence. The first nuclei of continents take shape not as grand masses, but as islands of stubborn lightness set within a restless oceanic floor. Heat flow remains high, so much so that the mantle refuses to keep quiet. Plumes rise from deeper layers, thin the lithosphere above, and feed provinces where flood lavas build plateaus in quick succession. Between these volcanic provinces, cooler regions sag under their own weight. Dense roots peel away from the underside of the new crust and drip back into the mantle, a foundry process that leaves the remaining rock lighter and better able to float. This delamination acts as a sculptor of foundations. What stays attached becomes the seed of a craton. What falls away returns as fuel for the next pulse of melting. Komatiite eruptions write a hotter signature on the surface. Ultramafic lavas run like rivers, liquid and quick, their temperatures high enough to glow even in daylight. They form spinifex textures as they cool, blades of olivine that lie like frozen grass within a matrix of dark, glassy minerals. These rocks testify to a mantle more energetic than any that will persist later. Where komatiites meet water, they quench into pillows and breccias, a fabric that later guides fluids and seeds or deposits. The contrast between these ancient flows and the paler granitoids marks the dynamic of the young crust, a dance of heavy and light, dense and buoyant, fast and steadfast. Segregation of the crust into domains produces stress at their edges. Microplates jostle, collide, and slide past one another along faults that knit together greenstone belts and granite domes. Greenstones carry the memory of deep submarine eruptions, of basaltic pillows, of iron-rich sediments, of volcanic ash turned to fine tufts. Granites and TTG suites carry the memory of slow cooling within thickened crust. Together, they make belts that arc across terrains like braided ribbons, folded and thrust into stacks by compressional forces that lack the global regularity of modern plate tectonics, yet achieve much the same architecture. The resulting metamorphism imprints minerals with pressure and temperature paths, garnet zoning that records burial and exhumation, amphibole chemistry that remembers fluids long gone. Partial melting becomes the quiet engine of growth. Basaltic crust submerges where it thickens or cools, its base heated and hydrated, until quartz-rich melts separate and rise. These melts strip incompatible elements from their source, elements that prefer liquid to solid, and carry them upward to become part of the lighter crust. Each cycle leaves the source more refractory, more resistant to further melting, while the upper levels gain silica and sodium that enhance buoyancy. Continental fragments thicken, cool, and strengthen, changing from rafts into keels that extend deep into the mantle. The keels stabilize convection above them, deflecting flow and protecting the crust above from easy recycling. Sediment joins the construction. Weather and water grind volcanic plateaus into sand and silt. Rivers collect the products of chemical weathering into clays and dissolved ions. Basins along the margins of rising blocks fill with layers that bury, compact, and cement into sandstone, shale, and chemical precipitates. These sediments load weak zones and drive subsidence, creating accommodation space for further deposition and for magmas to intrude. When compressional regimes return, the layered packages fold into anticlines and synclines, then break along thrusts that stack the strata into thickened wedges. The record of this deformation becomes a geological library, pages stitched by faults and written in mineralogy. Isostasy governs elevation. Thickened continental crust floats higher than surrounding oceanic lithosphere, not because it is lighter in total, but because its average density is lower and its thickness greater. Mountains rise where convergence occurs, and as they rise they erode, and as they erode they shed weight, and as they shed weight they rise further. Feedbacks operate without intent yet with precision. River systems find grades that carry material efficiently from highlands to basins. Delta complexes advance into shallow seas, their topset beds building outward while their foresets slip and stabilize. Gravity sorts particles by size and makes rhythm visible in crossbeds and graded beds that once moved in unseen currents. Metamorphic facies speak in a language of temperature and pressure. Blue schist signals rapid burial, with a cool gradient where water-rich rocks carry glaucophane and lawsonite. Granulite signals deep, dry heating where feldspars and pyroxenes dominate and biotite loses its volatiles to the passing flux. Eclogite records transformation of basalt into garnet and omphacite at mantle conditions, a reminder that subduction-like processes can exist even when the choreography of modern plates has not fully taken hold. Retrograde paths carry these assemblages back toward the surface along fractures where fluids return, replacing high-pressure minerals with lower-pressure cousins, smudging but not erasing the memory captured in texture and inclusion trails. Mantle dynamics adjust around the growing keels. Flow lines bend. Upwellings prefer the edges of cratons where the lithosphere thins. Rifts initiate along sutures of old collisions or along corridors where heat gathers beneath insulating plates. Continental fragments pull apart, form basins, invite seawater, then sometimes reverse and rejoin along different seams. Each opening spawns mafic intrusions, dikes and sills that rush upward, cool, and leave the crust both stronger and more fractured. Each closing knits together terrains with fabrics that can be read in magnetic signatures and in the orientation of minerals that remember stress. Ore systems begin to localize. Hydrothermal fluids circulate through faulted belts, leach metals from large volumes of rock, and deposit them where chemistry or pressure changes abruptly. Sulfide-rich veins form near volcanic centers. Banded iron formations lay down laminae where anoxic waters meet localized oxidants, dressing seabeds in alternating hematite and chert. Comatite channels concentrate nickel and platinum group elements along flow bases. Later, intrusions carry gold in quartz veins that cut across greenstones and plutons alike. The distribution of resources becomes a mosaic defined by heat, fluid movement, and the architecture of the young lithosphere. Surface relief grows varied as rigidity increases. Plateaus rise above lowlands, rift valleys etch long scars that host linear lakes. Volcanic cones punctuate plains with symmetrical slopes and crater lakes. Lava deltas extend coastlines in broad steps. Inland, pale granitic domes exfoliate into rounded tores as sheets peel away under daily thermal stress and chemical attack. Fresh fractures shine as clean plains where rock split in the last quake. Over time, the landscape acquires topography that forces climate to diversify over short distances. Rain shadows develop. Orographic storms wring moisture from winds where they climb. Basins trap fog and cold air while ridges bask under clearer skies. Seismicity teaches the land to move in fits. Fault systems connect like branching rivers, with main strands and subsidiary splays that slip by millimeters in most years and by meters in rare convulsions. Each event resets knolls and scarps, tilts lakes, and frees trapped fluids that race along the new porosity. Aftershocks tick like a fading clock. In deeper levels, ductile flow smooths sharp corners, but near the surface, brittle behavior rules. The contrast between slow creep at depth and sudden rupture above defines the style of deformation in a lithosphere learning both patience and surprise. Thermal budgets evolve toward moderation. Radiogenic heat wanes as short-lived isotopes fade. The mantle cools and becomes more viscous. Lithospheric plates thicken. The style of interaction shifts from subduction and dripping to something closer to continuous subduction along long margins. Once sustained, these systems recycle oceanic crust, draw down volatiles, and feed arcs that build new continental material through andesite and dacite additions. A feedback loop emerges where continents beget more continents by protecting their roots and by nourishing magmatism that thickens and stabilizes their margins. Magnetic behavior leaves tapestries in rocks. As lavas cool, iron-bearing minerals align with the prevailing field and freeze a record of direction and inclination. Granitic intrusions carry remnant signals locked in by slow cooling. Metamorphism can reset these records, but not always completely, so the fabric contains palimpsests that careful analysis can separate. Reversals of polarity punctuate the sequence, their timing written as alternating normal and reversed magnetization in dike swarms and flows. These data later provide maps of drift, rotation, and the assembly of larger landmasses from smaller bones. Water continues to influence mechanics. Hydrated minerals lower melting points in subducted slabs. Fluids released at depth trigger melting in the overlying mantle wedge and change the strength of rocks along faults. At shallow levels, pore pressure swings can flip a fault from locked to slipping. Clay minerals grown during weathering alter friction angles and lubricate slides. Even tiny amounts of water in crystal lattices change the viscosity of the mantle. The planet learns to couple its surface hydrosphere to its interior machinery through pathways that operate without intention and produce consequences that reshape the map. A sunrise over a proto-continent reveals a surface busy with quiet work. Granite domes glow pale pink, their feldspars catching the first light. Dark belts of metamorphosed volcanic rock thread the domes and hold valleys where mist collects. Rivers sparkle along fracture-controlled paths, then scatter into gravelly fans where slopes ease. In the distance, a rift lake lies in a long wound, its margins lined with fresh black dikes that stand like walls. Farther on, a line of plume-fed volcanoes lifts thin columns of steam into a calm sky. The air carries the smell of damp stone and faint sulfur. The ground feels firm underfoot, and the horizon suggests a body learning how to carry weight. The crust has ceased to be a mere lid and has become a living architecture, responsive to heat, gravity, and water. It builds, breaks, heals, and keeps what it can. Islands of buoyant rock coalesce into blocks that begin to resemble continents. Keels anchor them, rifts challenge them, plumes feed them. Subduction-like motions recycle their margins and add new layers to their edges. From this evolving stage, climate, ocean, and chemistry draw new options. The orchestra of geology gains sections and harmonies, and the score widens from percussion and brass to include strings and woodwinds that can sustain notes and weave motifs across deep time. Water moves across stone with the patience of a teacher. It dissolves, carries, sorts, and returns, then repeats until the landscape becomes a laboratory with a million benches. The solvent holds ions close, screens their charges, and invites collisions that would never occur in dry air. Heat rises from below, light falls from above, and the liquid medium mediates their arguments. Every eddy is a microreactor, every shoreline is an evaporator, every fracture is a pipeline that shuttles reagents from one world to another in moments measured by diffusion and flow. At mid-ocean ridges and flanks, cold brine enters cracks and descends. Pressure lifts its boiling point, temperature climbs, metals and sulfide join the ride, and the returning fluids billow into the sea as shimmering plumes. With each vent, water learns new chemistry. In one field, alkaline fluids spill from chimneys built of carbonate and brucite, rich in hydrogen and methane, their pH high, their warmth gentle compared to lava. In another district, black smokers roar hotter and more acidic, their jets metal-loaded and suffused with sulfide. Both environments stitch steep gradients into the ocean. Across a distance measured in centimeters, hydrogen activity changes by orders of magnitude, temperatures swing from near freezing to scalding, redox potential flips sign. The gradients are invitations written in invisible ink that glows for any chemistry ready to use them. Minerals at these interfaces offer catalytic surfaces. Iron sulfide forms maconite and greigite, with layered structures shot through with defect sites. Those imperfections hold electrons in ways that encourage transfers. Nickel and cobalt find perches within the lattice and provide gateways for hydrogen to meet carbon monoxide or carbon dioxide. On these facets, simple molecules assemble into more complex ones by pathways that feel almost metabolic. Carbonaceous chains grow by stepwise addition. Small aldehydes and acids appear and slide into new arrangements in the presence of metal centers that resemble cofactors. The scaffold is geologic. The reactions, though still blind, echo patterns that later become purposeful. In shallows and splash zones, the rhythm changes. Pools warm under sunlight, then cool as evening lifts heat into the sky. Evaporation concentrates solutes. Drying cracks expose more surface area and draw thin films across mineral grains. When water returns, either by tide or by rain, the films rehydrate and release products into a slightly different medium. This alternation drives chemistry that languishes at constant conditions. Monomers bump into one another on clay surfaces, aligned by charge, and join into short chains through dehydration reactions that water usually forbids. Phosphates, notoriously reluctant to react in dilute solution, become cooperative on hot surfaces where cations and minerals coax them into bonds that store energy. The ingredients arrive by many routes. Hydrogen and carbon dioxide come from vents, from serpentinizing rocks, and from the sky. Nitriles and aldehydes form under lightning and ultraviolet, and then wash into ponds and bays. Sulfur cycling between gas and mineral supplies, thioesters and sulfides that act as activating groups for condensation reactions. Meteorites deliver amino acids, purines, and fatty acids in assortments that reflect their parent bodies, a diaspora of organics that melt into water and change its inventory. Comets contribute volatiles that tilt the balance toward molecules that prefer cold synthesis and gentle warming. Each parcel of water receives a different subset of this library, and the world becomes a network of experiments running in parallel. Some locales favor the making of sugars. In alkaline pools charged with borate and calcium, simple formaldehyde can link into chains that bend toward ribose and its cousins, stabilized by the borate that holds their fragile backbones steady. Elsewhere, the same starting material veers toward tar in the absence of those guardians. Selection begins as a property of the setting long before molecules choose themselves. In other places, amino acids arise by pathways that pair cyanide with aldehydes and ammonia, then hydrolyze into stable products when water returns. The results settle into sediments or remain dissolved until currents move them to a place that can use them. Lipid-like molecules gather at interfaces. Fatty acids align at water surfaces with their tails in the air and their heads in the brine. When enough accumulate, they close into spheres that sequester a tiny volume of solution apart from the rest. These vesicles swell and shrink with changes in pH and salt. They fuse when bumped, they divide when sheared, they become leaky or tight depending on temperature and composition. Mineral grains covered by amphiphiles gain new personalities, turning from hydrophilic to hydrophobic, and back as coatings form and fall away. Wet-dry cycles promote ester linkage formation between alcohol and acid, creating more persistent membranes and scaffolds that scaffold other reactions. Cold plays a role that heat cannot. In winter bays and high-latitude shallows, water freezes from the top and pushes salts into veins and pockets within the ice. These eutectic zones become brines far more concentrated than the ocean beneath. Reactants forced together in these frozen corridors react at low temperatures that preserve delicate products. Ultraviolet light passes through clear ice with less scattering than through turbid water and triggers photochemistry along planar channels where geometry favors certain outcomes. When thaw arrives, the products flush into the sea in pulses that travel along density boundaries and disperse across continental shelves. Within rocky matrices, pores act as concentrators. Thermal gradients drive thermophoresis that pushes large molecules toward cooler regions or toward warmer ones, depending on size and solvent. In narrow channels, convection cells establish looped flows where a solute repeatedly visits hot and cold zones within seconds, a built-in cycling that mimics laboratory protocols without design. In carbonate chimneys, thin walls separate two waters of opposing chemical temperament. Protons cross where minerals permit, electrons hop where sulfide lattices conduct, and ions migrate until their gradients diminish. Once the gradients exist, any structure that allows them to do useful work gains advantage in persistence, even if usefulness is still defined solely by survival of the arrangement itself. Chirality begins to skew in subtle ways. Crystal faces on certain minerals prefer one hand over the other when they host adsorption. Light that scatters off aerosols at glancing angles becomes ever so slightly circularly polarized and can break one enantiomer more readily than its mirror. Stirring in vortices separates left-handed and right-handed molecules by preference so small that only time brings it into view. Ice surfaces and clay interlayers act as sieves that let one orientation slip more easily through. None of these biases guarantee dominance, but together they push a system away from perfect symmetry. And in chemistry, as in weather, symmetry is seldom stable when flow is involved. Phosphorus finds pathways that overcome its stubbornness. Reduced phosphides delivered by iron-rich meteorites react with water to form phosphite and other soluble species that travel where orthophosphate would stagnate. Lightning strikes fuse soils into glasses that trap phosphate in forms that release under specific pH changes. Iron minerals exchange their anions at the right surfaces and hand off phosphate to organics that can hold it. In hot puddles, condensations assemble energy-rich bonds that persist until dispersed. Energy becomes a currency, as much as a product, stored in arrangements that boost the odds of further assembly when conditions allow. Nitrogen chemistry enriches the broth. Atmospheric nitrogen resists reaction, yet in the presence of lightning, shock, or ultraviolet catalysis, it yields small amounts of ammonia and nitriles. In hydrothermal conditions, iron and nickel surfaces bind nitrogen species and lower barriers that otherwise would be too high. These fixed forms dissolve, complex with metals, and enter reactions that build bases, amino acids, and small amines that change local pH and reactivity. The cycle closes not by biology but by mineral and photon, a slower circuit with many leaks but no single point of failure. Feedbacks appear that have nothing to do with intention. A pool that runs slightly alkaline encourages fatty acids to assemble, which then strengthen the boundary that holds alkalinity within. A vent that produces hydrogen maintains redox gradients that drive carbon fixation on its walls, and the products change the conductivity of the mineral, which then alters the gradient. A shoreline caked with evaporites dissolves in storms and raises ionic strength, which shifts colloids into gels that trap more particles, which then increase evaporation by darkening the surface. The environment amplifies its own preferences by 1,000 small loops that persist because they are stable, not because they are mindful. Occasional catastrophes write punctuation into the chemical story. An impact drops dust into the sea and brings a wave of metals that briefly poisons certain reactions while enabling others. A volcanic episode vents chloride so strongly that pools turn briny and force lipids to collapse into layered films that, once rinsed, reassemble into vesicles more robust than before. A long, calm period lets sediments accumulate undisturbed, and within those layers pressure squeezes fluids that emerge later along new faults charged with products distilled by burial. Nothing proceeds in a straight line, yet trends emerge when time is allowed to stretch. Energy arrives in many coins: photons, heat, and split bonds. Chemical gradients donate electrons or accept them. Mechanical forces grind mineral surfaces and expose fresh reactive planes. Radioactive decay warms pore waters and creates radicals in passing. The medium navigates all of this without plan. Structures that can absorb energy without falling apart last longer than those that cannot. Molecules that can spread energy across their bonds avoid breaking and are more likely to bounce into the next reaction intact. Assemblies that couple an unfavorable step to a favorable one collect into niches where their cycles close, at least partly, and closure is the seed of stability. Along an inlet lined with basaltic glass that has weathered into soft palagonite, a film of water thins under morning light. Salt crystals begin to grow along its edge like snowflakes with square habits. In the center of the film, tiny bubbles form around motes of clay. A breeze sweeps across and curls the film into wrinkled ridges that trap pockets of liquid in repeating cells. Within each cell, the concentrations differ slightly. One holds more aldehyde, one more phosphate, one more iron, one a few extra fatty acids stolen from a wave. The arrangement is not purposeful, yet it is not random either. Geometry dictates differences, and differences dictate reaction paths. A gull would not yet exist to cast a shadow across this scene, but if one had, the shadow would have crossed 100 small laboratories in a single heartbeat. When evening returns, the pools cool and thicken. Vesicles seeded by the day's chemistry bump and merge and divide under the mild kneading of incoming tide. On a nearby bench, a crust of salts locks away molecules until the next rain breaks it. Far below, along a chimney rim, hydrogen sighs through iron sulfide plates and leaves behind traces of carbon that layer the mineral in a thin varnish. Overhead, stars appear and send a sparse rain of energetic particles through the high air, a reminder that even the quiet night is full of reactive influence. Water keeps its counsel. It simply continues. flowing where gravity calls, rising as vapor where heat insists, and returning as rain with a memory of every place it has been. Light lands on minerals and wakes their hidden talents. Photons strike sulfides and oxides and lift electrons into motion that was impossible in darkness. Zinc sulfide throws off reducing power when ultraviolet arrives, a semiconducting plane turned into an engine for electron transfer. Rutile and anatase accept energy and pass it into bound water, splitting molecules that otherwise resist. On iron sulfide faces, defect sites host charges long enough to encourage carbon dioxide to accept electrons and slide towards small organics. The surface becomes a panel of tiny junctions where light converts into chemistry, a harvest measured not in watts but in rearrangements of bonds. Lightning serves as the impatient sculptor of air and sea. Charge separation grows within storm towers until the voltage stands taller than mountains. When discharge comes, the path carves channels through humid sky and changes nitrogen into nitric oxide in a breath of heat. The shock sets pressure waves running that compress droplets and force reactions in their skins. On the ground, fulgurites freeze a record of the bolt as glassy tubes that lock in metal vapors and trapped gases. Their interiors capture residues that wash free with the next rain and seed nearby pools with reactive species. A single storm writes a map of altered reactivity across a coastline, a constellation of hotspots that dissolve slowly into the broader medium. Impacts deliver heat and pressure in a language chemistry understands. Shock waves fold simple molecules into chains and rings before the heat fades. In ejector curtains, condensed dust gathers onto larger grains while still hot enough for catalysis. When the fragments land in shallow water, they hiss and spall, creating cavitation that collapses bubbles with microbursts of temperature and pressure. Those collapses, like tiny stars, provide moments where stubborn reactions leap forward. Sonochemistry extends wherever waves pound cliffs and reefs of glass, each crash squeezing and releasing water until radicals appear and vanish in pulses timed by surf. Mechanical energy engraves rock with charge. As faults slip and grind, minerals strain and polarize. Quartz responds with piezoelectric fields that spark at microscopic tips. The flash of electrons across newly opened fractures reduces ions at one grain and oxidizes them at the next, a flicker of redox that fades as soon as stress eases. In volcanic ash clouds, grains rub and exchange charge, building to discharges that stitch the plume with crackling veins. These sparks rain oxidants and reduce species onto slopes and deltas where ash meets water. Even landslides create electrical whispers that momentarily rearrange local chemistry. Thermal gradients open doors that constant heat keeps closed. Along chimney walls, centimeters separate scalding interiors from chilled seawater. Catalytic minerals sit across that span and shuttle protons and electrons in opposite directions, a natural diodic architecture that favors stepwise assembly. In porous rocks near hot springs, convection cells draw fluids through loops that pass repeatedly from hot to cool. Each cycle asks molecules to test a bond, break it, and make another, a form of combinatorial search biased by the geometry of the pores and the cadence of heat flow. Far below, radiogenic heat seeps from rocks rich in potassium and uranium and warms films on grain boundaries where diffusion is king. Radiolysis creates fuel in darkness. Particles born from decay streak through water films and leave behind trails of hydrogen and peroxide. Within fracture networks, those products meet iron and sulfur and generate gradients strong enough to drive reduction of carbon dioxide. In deep crustal aquifers cut off from the surface for ages, hydrogen accumulates until it leaks toward reactive hosts. The rock becomes a slow battery. Its discharge travels through tiny conduits lined with minerals that select which reactions can spend the stored energy. Ionizing radiation does not need to be intense to matter. It needs only to be persistent, and persistence is the signature of stone. Tides grind energy into coastlines. A close moon lifts the ocean into broad bulges that sweep across shelves and race through narrows. Friction at the seafloor turns some of that motion into heat and turbulence. In tidal inlets, currents reverse with clockwork reliability, exposing flats to air and then drowning them with brine. Films assemble, and rupture in synchrony with the phases of the sky. In rocky pools, water levels rise and fall by handspans, straining vesicle membranes and forcing them to take up solutes when stretched, then to expel them when compressed. This cycling of concentration acts like a pump, a mechanical method for moving molecules up the hill of unfavorable equilibria. Solar variability adds texture to the canvas. The young star flickers, not wildly, but enough that ultraviolet intensity creeps up and down over years and decades. During brighter spells, photolysis creates more radicals in the upper air and more fixed nitrogen that rinses into the sea. During quieter intervals, haze clears and deeper waters warm, changing the reach of light into the column. Subtle shifts in spectral balance alter which minerals work best as photocatalysts. Zinc sulfide thrives under harder ultraviolet. Iron oxides prefer a hint of longer wavelengths that scatter through haze. The spectrum writes preferences into the patchwork of shorelines and vents, without a single conscious choice. Electrochemical cells appear wherever gradients meet conductive paths. Sulfide minerals paired with graphite grains, in a saturated bed, form natural half cells. When connected by a film, electrons crawl from one to the other, while ions drift through the liquid to keep charge balanced. Slight differences in composition between adjacent brine pockets turn adjoining pores into a network of tiny batteries. Some discharge in seconds, others in days, leaving behind trails of reduced carbon or oxidized sulfur that alter the next round of reactions. The landscape behaves like an analog computer with no output other than the reshaping of chemistry within it. Day and night carve rhythms that matter beyond warmth and cold. Light reactive molecules form when the sun is up and break when it is down. If a molecule can copy itself faster than light can erase it, it persists into evening and gains a head start the next morning. If a membrane holds together through the dark, it wakes to another day of influx. Selection emerges from schedule. Reactions that tolerate dusk and dawn outlast those that require a fixed temperature and a fixed beam. Season adds another layer. Longer days concentrate photochemistry into high latitudes during some months and release that advantage to other latitudes in others. The planet sweeps a balance wheel through a year and sets a rhythm clock that compartments learn to keep. Mineral band gaps set thresholds that light must cross. If a photon is too weak, it passes as a courtesy. If it is strong enough, it lifts an electron that can flee across a defect and become work. Grain size tunes this behavior. Nanoscale particles respond to different wavelengths than their bulk parents. Weathering reduces large crystals into flakes and needles that widen the window where photochemistry can occur. A beach of mixed sands becomes a spectrum splitter. Dark magnetite warms and drives convection in the top millimeter, while pale feldspar reflects, cooling the film above it. Patches of zinc sulfide and titanium oxide act as microreactors only when the right color lands. The surface functions as a mosaic of tools, laid out by geology and arranged by erosion. Energy can arrive gently enough to let fragile intermediates survive. Scattered light inside a haze-rich sky comes as a soft bath of photons rather than harsh beams. Under such illumination, one electron transfers occur without the scorched side reactions that hard ultraviolet forces. In shallow depths, water absorbs the highest energies but passes the mid-range. That mid-range reaches catalytic phases that can couple reduction of carbon dioxide to oxidation of sulfide without tearing everything apart. The balance matters. A world that gives only violence makes tar. A world that gives only calm makes nothing. The mix here provides sparks and cradles, blows and shelters. Electrostatic fields gather where mist meets rock. As sprays dry on mineral faces, ions stick more than their companions, leaving charged patches that steer incoming molecules. A negatively charged patch attracts protonated amines and favors amide formation in the presence of activated acids. A positively charged patch draws carboxylates and arranges them into lines that favor head-to-tail links. When fog returns, the pattern washes away and can be written anew. The script is temporary, but legible to chemistry. Over many cycles, surfaces that happen to favor productive pathways will accumulate products that change the surface again, a bootstrapping into more complex mosaics. Cosmic particles seed ion pairs in the high air that cascade into lower layers by recombination chains. These cascades alter how droplets grow, when clouds form, and where they rain. The chain ends by modifying the radiative balance of an afternoon or the timing of a storm. That timing changes which shore gets drenched and which remains dry, which pool dries down to a gel and which stays dilute. Even distant influences become local through water, wind, and light. On nights when meteors whisper across the sky, sodium and iron atoms linger in the mesosphere and tweak the chemistry of the thin layers above. Nothing is isolated. Every field of energy reaches for matter somehow. Along a basalt bench dotted with pale patches of zinc sulfide, sunrise arrives as a thin blade through low haze. The first photons strike and release electrons that skitter into water films. Nearby, a splash of tide leaves bubbles that survive for minutes before popping, their skins covered in amphiphiles that hold voltage across micrometers. A breeze brings a taste of volcanic sulfur, and the film thickens with sulfide. The combination encourages carbon dioxide to accept electrons and become formate, not in a mass, but in countless tiny acts. A cloud slides over the sun, and the reaction slows without stopping. When light returns, the process resumes from where it paused, as if the bench kept a quiet memory of the morning. By evening, the day's products have drifted toward low spots and accumulated against a ridge of salt that blocks their escape. A faint crackle passes through the film as the temperature falls and minerals contract. That flash of charge finishes a few reactions that lacked only a gentle push. Night settles, the bench cools, dew forms. Moonrise tilts the tide and sends a slow sheet of water to collect the residues and move them to a new arena. Energy has arrived by light, by shock, by friction, by decay, by tide. None of it carried intention, all of it carried possibility, and possibility is the first tool a planet offers to matter. Space keeps a ledger of gifts and scars, and the planet reads it as rain that burns and stones that whisper. Dust falls almost constantly, a sift of dark flour blown from asteroid collisions and comet tails. Each grain is a capsule of ancient ice and refractory mineral, its surface smoked by starlight, its interior patient as a seed. In the high air, grains slow against dense molecules and warm enough to release trapped gases without turning to plasma. Organic films survive this descent, unspooling aldehydes, nitriles, and aromatic rings into thin clouds that drift downward with the next weather. The quiet drizzle matters more than spectacle. It writes chemistry into the sky day after day, then hands the writing to water. Larger visitors come with their own grammar. Carbonaceous bodies arrive soft by cosmic standards, fragile aggregates of phyllosilicates, carbonates, and embedded organics wrapped around ice. Their entry can be merciful when geometry and speed permit. Ablation peels their skin in glowing sheets, while the core stays cool enough that amino acids and sugars remain intact. When these pieces break in the lower atmosphere, they scatter as a rain of fragments that hiss when they meet wet ground. In shallows and lakes, the shards bleed soluble compounds that color the water faintly brown and scent it with hints of oil and bitter almond. The shore receives a line of dark pebbles under the foam, a harvest from a snowball that began its life among unlit stones. Metallic bodies deliver a different cargo. Iron and nickel cores from shattered planetesimals slam into the crust and leave behind regmaglyptid masses that weather into rusty sculptures. Within them, the mineral schreibesite glints where fractures cut, a phosphide that reacts with water to form phosphite and hypophosphite. Those reduced species leap into reactions that orthophosphate would refuse, weaving energy-rich bonds into organics at temperatures found in tide pools and heated soils. As weather lifts phosphite into streams, it meets clays downstream that hold it long enough for further condensation. A meteorite that looks like a statue becomes a slow factory, its output measured in invisible bonds rather than metal. Comets complicate the recipe. Their ices carry carbon monoxide, carbon dioxide, ammonia, methanol, and traces of more elaborate molecules that formed in the freeze of interstellar clouds. When a nucleus breaks near perigee, icy fragments sublimate into gas and dust, and some reach the ground as a snow that never was snow. The mix soaks into porous ash around vents and feeds reactions that prefer cold starts and gentle warming. In the thin films coating mineral grains, ultraviolet carves complex pathways through these imported volatiles, making radicals that add to double bonds and build rings that would be difficult in bulk solution. The residue tastes like smoke and chemistry. It stains rock with a varnish that rain cannot scrub away in a single season. Impacts dig wells that steam. A stony projectile scoops a crater, shatters bedrock, and leaves a heat reservoir buried beneath shattered lids. Water finds the hot core along fractures and returns to the surface in springs that run for centuries. These craters become lakes, their floors breathing warm currents through sediments charged with nickel, cobalt, and iron newly exposed by the event. Hydrothermal vents along the ring faults deposit sulfides in black ribs that look like charred wood. Pores in the breccia bind organics that drift in from the catchment and hold them near catalysts lining the cracks. An impact makes a wound that quickly becomes a laboratory fed by both sky and stone. The young giant planets are not innocent bystanders. Their gravity sculpts the flow of debris, flinging some bodies outward, herding others inward, and occasionally orchestrating showers when resonances align. Swarms of comets sweep through the inner system after a distant ripple travels the Oort cloud. The streaks appear for a few nights and then vanish, but the chemistry they drop lingers in soils and surf for generations of storms. Jupiter protects as much as it sends, swallowing paths that might otherwise meet the inner planets. The balance is delicate. Too much delivery turns oceans into tar and skies into curtains of smoke. Too little delivery starves experiments that need exotic catalysts and volatiles. The tally that plays out favors variety without smothering it. Interplanetary dust particles carry metals in unusual oxidation states and silicates laced with tiny inclusions of magnetite and sulfide. On contact with water, they release peroxide and superoxide species that oxidize organics gently. Gentle is important. Harsh oxidants destroy as much as they make. Mild ones nudge systems toward diversity without erasing what forms. The dust also brings grain sizes perfect for templates. Scales of tens of nanometers to a few micrometers offer surfaces where ions line up in ways that favor particular linkages. When these particles settle onto a clay bank, they increase its catalytic vocabulary without altering its mineral name. A different conveyor arrives with micrometeorites that survive as glassy spheres. They fall into the sea and snow through the water column as shining beads. As they cool, internal stresses crack them with networks that admit seawater and release soluble metals over time. Their surfaces bloom with iron oxides that catalyze reactions at the microlayer between air and sea. Winds push these spheres into lines along slicks where foam gathers, and there they act as anchors for films that concentrate amphiphiles. A necklace of glass and oil circles a bay and traps a suite of molecules until the next wave breaks the strand and starts the loop again. Tholin-like substances form where methane and nitrogen-rich plumes meet ultraviolet and particles in the upper air. They settle as a fine haze that drifts down over continents and oceans alike, a brown deposit that changes the albedo of snowfields and the wetting behavior of rocks. In pools, this material becomes a feedstock for reactions that love nitriles and unsaturated bonds. Under a gentle bake, it releases amines and acids, and it glues silt into fragile crusts that crack into hexagons under the noon sundae. Each crack becomes a microbasin where brine lingers a few hours longer than outside, and a few hours is enough when cycles repeat for years. The isotopic fingerprints of delivered water complicate the balance in the ocean. Some cometary ices carry heavier hydrogen ratios than the sea, while hydrated minerals from certain asteroids lean closer to the ocean's eventual value. As these sources mix, the planet's inventory of hydrogen and oxygen shifts within narrow bounds. The ocean's flavor does not swing wildly, but it drifts, and that drift changes vapor pressures and condensation patterns in subtle ways. Mountain snowfall lines creep, storm tracks shift, and some basins linger longer in drought between volcanic bursts. Delivery from space writes on the climate in handwriting small enough to go unnoticed by hills but large enough for cycles to sense. Entry mechanics decide survivorship. A shallow angle spreads heating over time and leaves organics with a chance. A steep fall compresses air into a plasma that disassembles delicate molecules before they can kiss the sea. Porous projectiles buffer shock by crushing internally, a sacrificial deformation that gives chemistry a chance to see dawn. Dense metal spares its core by shedding skins. Stony meteors crack and spray fragments that cool rapidly as they tumble. Every arrival is a negotiation between shape, speed, mass, and atmosphere. The planet's thick sky acts as editor, refusing some drafts and letting others through with corrections scrawled in fire. Oceanic delivery does not end at the surface. Turbulence drags dissolved organics downward, with spindrift and collapsing bubbles. Marine snow binds grains and organics into flocks that sink through layers where temperature and chemistry change with depth. At thermoclines, sinking slows, and material lingers where microbes might one day gather. For now, minerals do the work, catalyzing slow transformations in dim light or in darkness. On the seafloor, impact spherules and dust settle into a soft fabric that blankets basalts and chemical sediments alike. Percolating fluids leach products and deliver them to vents and fault scarps, where heat can take the next step. On land, impact melt sheets glass the ground into planes that resist weathering for a time. Pools collect along their edges and take on the character of the glass. Silica-rich surfaces neutralize acids and promote condensation where carbonyls and amines meet. Volatile, rich glass moderates dehydration reactions by slowly releasing water as it devitrifies. In the shadow of crater rims, frost lingers in morning, even in warm climates, extending the window for ice chemistry to perform its peculiar tricks with eutectic brines and planar channels. Sunlight sweeps across and resumes the day shift when the shadows retreat. Sometimes a bolide punches through the ocean and delivers vapor to the upper air, where it condenses as noctilucent veils that shimmer after sunset. Within those veils, ionic chemistry dances through rarefied paths. The products settle days later and fall like a second, invisible rain, carrying oxidants and reduced nitrogen to deserts that rarely see water. These thin deposits coat rocks with films that alter the first minutes of any storm, when the initial droplets dissolve and release their cargoes into rivulets. The first minutes of a storm are different from the last, and cosmic influence often walks in the door early. A night on a broad plain ends with a sound like a low drum roll. A fireball crosses the sky and blossoms into a scattered cluster of red sparks. Hours later, a peppering of stones lies warm on the ground. In a nearby marsh, fragments hiss and settle into the muck. By morning, an oily sheen spreads in threads from the impact points, reflecting the sun in a broken mirror. In a week, nothing obvious remains except stones and subtle stains in the sediment. In a year, organics derived from those stones have washed into a channel that feeds a bay. In a decade, none of the people who might have noticed exist. The chemistry remains, woven into films on grains and bound within clays, moving with tides and storms from margin to margin. Space does not simply wound, it furnishes, perturbs, instructs, and seasons. Each grain and boulder writes a line into a sprawling script composed of water, rock, and light. The accumulation of small deliveries outweighs the headlines carved by craters. The recipe changes by teaspoons rather than cauldrons, and teaspoons are enough when time is long. Somewhere between the chill of distant comets and the heat of impact cores, a planet learns to fold alien material into native processes until the distinction fades. The sky receives, the sea dissolves, the crust reacts, and the ledger grows thick with marginal notes that only chemistry can read. Crystals act as archivists when rock forgets. Among the toughest of them, zircon keeps the minutes of a very old meeting between heat and water. Its lattice of zirconium, silicon, and oxygen admits a few imposters that change its fate. Uranium slips into zirconium sites and begins to decay on a schedule that nothing in geology can hurry or delay. Lead accumulates as the daughter of this process and remains trapped unless the crystal cracks. The ratio between parent and child marks ages with a precision that survives metamorphism, subduction, and the indignities of deep time. A grain smaller than a sand mote can carry a page of history long after the page it came from has been burned and rewritten. In an ancient belt of weathered sediments later cooked into gneiss, rounded zircons rest like beads gathered by a patient river. They are not from the rocks that hold them now. They were eroded from older terrains that must have stood as hills and mountains long gone. Each grain shows concentric zones under cathodoluminescence, rings that speak of pulses of crystallization in magmas that cooled slowly. Within those rings, tiny inclusions of quartz and feldspar lie like whispers about the melt that hosted them. The parent was not a simple basalt. It resembled granitic melts that concentrate silica and sodium, melts that require crustal recycling or water-rich conditions to form. When these grains are plucked into a laboratory and touched by an ion beam, atoms leap from concentric zones and tell their story. The uranium to lead system gives ages that cluster far beyond most continental rocks. Some numbers begin with a 4 and are followed by strings of zeros that stretch imagination. A Concordia diagram plots these ratios as points that lie along graceful curves when the system has been closed. Some points stray because time and temperature have moved lead atoms into clusters along dislocations. Even those strays can be coaxed back to the truth by atom probe measurements that reveal nanospheres of radiogenic lead trapped like dew on invisible threads. While the dates fix a minimum time of crust formation, oxygen hides a different message within the same crystals. The proportion of heavy oxygen to light oxygen in zircon reflects the water that surrounded the magma before the crystal grew. Values higher than a particular mantle reference imply that the melt interacted with surface water that had exchanged with rocks at low temperatures. The implication is delicate and profound. Liquid water did not simply spill across basins. It returned to depth by weathering and melting and left its isotopic signature in granitic parents at temperatures far from volcanic extremes. A planet in that condition already ran a hydrologic cycle robust enough to alter crust and return its memory to new minerals. Titanium within zircon offers a thermometer when the pressure is known or when reasonable bounds can be set. Measurements suggest growth at temperatures cooler than the furnaces that feed modern basaltic eruptions. Such values align with the idea of silica-rich magmas forming in thickened crust under a sky with oceans. The numbers are not proof of lakes and clouds by themselves, yet they match a picture in which the surface hosted weather that could erode and a crust that could rise high enough to feel the chill of elevation. Hafnium isotopes provide a watch with a different face. Lutetium decays to hafnium, and the balance between isotopes can point to the time when source rock separated from the mantle. In zircons of extreme age, hafnium tells that the source separated early, implying that continental-like crust formed quickly after accretion settled. Rapid differentiation into buoyant continents and dense oceanic materials fits the idea that tectonic styles were vigorous, that melts rose and crystallized, and that erosion had targets to attack. The circle between crust creation, weathering, sedimentation, and remelting closes easily when this balance is considered. Within the crystals, inclusions speak softly but clearly. Quartz grains announce a silica-rich home. Muscovite flakes whisper of water in the melt. Rutile needles indicate titanium-saturated conditions at specific pressures. Some zircons carry apatite that hosts chlorine and fluorine, pointing to volatile content in the magma. The suite looks like chemical handwriting from felsic sources consistent with proto-continental crust. The grains act as suitcases packed with clues about where they were born. The sediments that embraced these zircons must have been carried by rivers that existed long before the rocks were metamorphosed. Rounded shapes tell of tumbles across stream beds and beaches. Sorting implies shorelines and currents. In the archive of a single grain lies the echo of rain-carving hills, of deltas advancing into shallow seas, of currents riffling sand, and of chemical weathering extracting ions into the water cycle. If a single crystal with these traits exists, more must have. The record that survives is a biased sample ruled by luck, but it is enough to sketch a surface that already wore the marks of climate and topography. Elsewhere, ancient tonalites and granodiorites hold zircons that fix ages only slightly younger. Their textures describe deep crustal kitchens where amphibole and feldspar stacked into mosaics. The chemistry of rare earth elements within zircons maps the redox state and the availability of cerium and europium during growth. Cerium anomalies hint at the presence of oxidized conditions in the magma. Europium behavior reflects plagioclase fractionation, a sign that crystallization paths had time to segment and settle. None of this demands biology. It demands patience and cycles that last long enough for minerals to sort themselves under gravity and heat. Not all information survives the furnace of metamorphism, but zircon endures. Even when rocks reach conditions where feldspars dissolve and new fabrics grow, these grains persist and keep their clocks. Occasionally they crack, and through those paths lead migrates. The damage is legible under the microscope as chains of disturbed zones that can be avoided by careful analytical beams. Thermal events later in history plant overgrowths on older cores, thin rims that date a different story. These layered crystals become timelines, core ages fixed in one epoch, rims in another, allowing reconstruction of multiple chapters in a terrain's evolution. Deep within some grains, a pattern of dislocations reveals the paths of alpha recoil, where uranium and thorium knocked atoms out of place as they decayed. Along those paths, nanoclusters of lead aggregate, high-resolution tools can see these tiny gatherings and measure their isotopic composition. The clusters confirm that lead production has been occurring in place for immense spans, not introduced later by fluids. This nanoscopic evidence supports macroscopic conclusions, a pleasing convergence across scales. Other minerals try to speak in these oldest terrains. Detrital monazite records episodes of heating and phosphorus-rich fluids. Apatite retains fission tracks that lengthen or fade according to thermal history. Zircon remains the primary archivist because it holds its contents across temperatures that erase these other messages, yet the chorus of lesser voices clarifies the melody. When all are taken together, a picture emerges of surface waters, sediment loops, and granitic assembly, while the sun still burned fainter than it does now. The ancient age itself presents a puzzle of survival. Crust older than the very old zircons is scarce on the surface today. Plate motions, melting, and impact gardening recycle and erase. That such grains remain suggests that their hosts spent much time in the deep interior of continents where keels protect them from return to the mantle. When uplift finally delivered them to erosion, rivers delivered them to basins that would eventually be compressed, heated, and exposed again by the shuffling of terrains. The journey is long and tortuous, and yet the clocks still tick when a beam reads them. A valley of low hills contains a stream that has cut into banded gneiss and greenstone. In a gravel bar gleam a few translucent grains among the dull quartz. A geologist kneels and swirls them in a pan until the heavy fraction concentrates. Among magnetite and ilmenite lie tough, bright prisms. Under magnification, their growth rings resemble tree rings, and their interiors carry tiny lakes of quartz. They are small and unremarkable to the eye, but their ages span back to a time when the world was still settling from its fiery youth. Count their isotopes, and the numbers recite a staccato poem of heat, water, and crustal strength. From a single crystal one can infer landscapes lost, storms unwitnessed, and continents resting under warm rain. The story is not told in spectacle but in ratios, in slight enrichments of heavy oxygen, in temperatures lower than expected, in hafnium that has travelled far from its mantle berth. The evidence aligns into a claim that oceans were already making weather, that rivers were already carving, that granites were already freezing at depths beneath mountains whose names have no letters. Zircon keeps that claim with a stubbornness that commands attention. Evening light makes the grains glow faintly on a laboratory stub as an ion probe pauses. Outside the window, rain taps against glass. Inside the chamber, a single crystal yields the last of its secrets for the day. Numbers scroll on a screen and settle into a curve that meet with those already measured. The curve bends along a path that points to a world with clouds, with shorelines, with granitic kitchens under pressure, and with water that had time to percolate and return. The page is small, the chapter is immense. The archivist has done its work with patience no living thing could match. The star at the center shines softer than memory would guess. Its fusion engine has not yet swelled to present power, so the light that falls on the planet is gentler by a quarter, a pale furnace compared to the blaze it will become. By simple arithmetic, Seas should stiffen into lids and continents should wear white armor from shore to shore, yet water remains loose and loud. Waves travel, rain falls, rivers dare gravity. Warmth persists in defiance of the quieter sun, and the reasons gather from stone, sky, and the hidden budgets of heat that move invisibly through air and ocean. Carbon dioxide shoulders much of the burden. Volcanoes exhale it with patience while the surface is still young. Without forests to drink it and bury it as wood, without shells to hide it in limestone on a global scale, the gas accumulates and thickens the blanket that turns infrared back toward the ground. The effect grows stronger as pressure increases. Molecules jostle and broaden their absorption lines so that wavelengths once allowed to escape are now intercepted and returned. Nitrogen, a gas content to watch, participates by presence alone, deepening pressure and multiplying the reach of carbon dioxide's long-wave grip. Water vapor joins wherever oceans are warm. It carries an immediate response to any spark of heating, a fast positive feedback that saturates the lower sky. Clouds assemble from this moisture, and their character decides whether light is reflected or heat is trapped. Thick bright decks cool the surface by turning sunlight aside. High icy veils warm by returning infrared downward. The balance never freezes into a single choice. Storms raise towers that cast shadows at noon and hold heat at night. Fog slides across saline flats and blurs the boundary between air and sea. Even without life, the hydrologic cycle learns to regulate, sharing energy between phases and altitudes with a precision that looks deliberate only because it endures. Methane offers a different kind of help. Serpentinizing rocks in the oceanic crust generate hydrogen that reduces carbon dioxide to methane in hotspots where fluids meet catalytic metals. Subaerial volcanoes release methane in smaller pulses. Under a sky with little oxygen, methane's lifetime lengthens, letting concentrations climb high enough to matter. Ultraviolet will eventually cut these molecules apart, but not before they have captured bands of infrared that carbon dioxide leaves untouched. Sometimes the same photochemistry that hurts methane builds a haze of complex aerosols. This haze raises planetary albedo and cools the surface like a translucent parasol. Then volcanism intensifies, methane grows, the haze thins, and the greenhouse recovers. The climate does not choose a single sign. It oscillates between competing tendencies and lands, more often than not, within a corridor where seas refuse to lock. Ammonia tempts with stronger greenhouse potential, though its sensitivity to ultraviolet makes it a fleeting contributor, except under heavy hazes or within sheltered boundary layers. Hydrogen itself, unreactive in the low air, interacts with nitrogen to produce collision-induced absorption that mildly warms the planet when pressures are high. Small effects add when the margins between freeze and flow are narrow. Even a shallow boost in infrared trapping can decide whether a bay remains liquid through winter or a cloud deck survives just long enough to hold the night. Geothermal heat plays a quiet role below the threshold of drama. Decay of potassium, thorium, and uranium supplies a constant trickle of energy from within. The flux is greater in a young planet than it will be in old age, and while it cannot replace a sun, it can lift deep ocean waters a few degrees and keep hydrothermal systems pumping in many neighborhoods at once. This background warmth counteracts the deepest chill, ensuring that if ice advances anywhere, it finds beneath it water that flows, not rock that shatters under the pressure of cold. Ocean dynamics help translate small advantages into big outcomes. With little land to block circulation, currents wrap the globe with fewer interruptions. Warm surface waters can travel freely until winds turn them downward and deliver their heat to depth. Upwelling returns modified waters to the surface in new latitudes, where air picks up energy and humidity. The turnover time of the young oceans may be shorter, their stratification thinner, their capacity to move heat poleward more vigorous. Gyres smear temperature gradients and resist the formation of continent-wide ice. Where ice forms, it drifts into warmer currents and thins, reinforcing the habit of liquid. Land area affects weathering, and weathering controls carbon. The conversion of silicate minerals into clays draws carbon dioxide from the air and delivers bicarbonate to the sea, where it eventually becomes carbonate minerals. If land is scarce, the global capacity to pull down carbon is limited. High temperatures and heavy rains speed individual reactions, but total area sets the ceiling. A small continental footprint keeps more carbon in air than a large one would, fortifying the greenhouse despite a softer Sunday. At the same time, seafloor weathering under warm water runs its own loop, but the exchange is tempered by hydrothermal fluid chemistry that does not always force carbon into lasting stone. Thermostats exist, yet their settings differ from later epochs. The lapse rate sets how quickly air cools with height, and moisture modifies this rate. A moist troposphere cools more slowly upward than a dry one because condensation releases latent heat. That single thermodynamic truth makes mountains less frigid and storm tops warmer, tipping the radiation budget toward retention. More water in the air means more latent heat released on ascent and more infrared emitted downward from cloud tops. The shape of the temperature profile becomes a lever that subtle gas changes can pull. Rotation reshapes winds and storms. A shorter day sharpens Coriolis forces that split circulation into more cells from equator to pole. The boundaries between cells generate persistent wind belts that steer currents and clouds. Where rising motion dominates, moisture gathers and high clouds trap heat by night. Where subsidence rules, skies clear, and sunlight warms the surface unhindered until dusk. The map of these zones migrates with seasons and with volcanic perturbations. Climate arises from statistics of these motions, not from a single average sky. Albedo seldom stands still. Fresh basalt presents a dark face. Ash deposits grey out the ground and soak light. Newly fallen snow blazes with reflectivity. Salty crusts glare beneath midday. Dust from impacts or deserts lifts into the air and shifts the color of sunlight that reaches the ground. Sea ice spreads and recedes, concentrating brine into channels that darken, then flushing to leave white again. Even puddles matter, because 1,000 small mirrors change the angle at which radiation is absorbed. When darker surfaces dominate, absorbed energy climbs. When bright veneers spread, reflection wins and temperatures fall. The interplay writes patterns with no author beyond physics. The carbonate system of the ocean mediates the exchange of carbon between sea and sky. Alkalinity, controlled by the sum of bases delivered by weathering and by hydrothermal processes, sets how much carbon dioxide the ocean can store for a given pH. Temperature then decides which way the balance tips in a given season or region. Warm water holds less gas and exhales. Cool water inhales. If currents carry cool water into sunlight, it warms and releases. If winds force warm water to rise from depth, it cools and absorbs. These breathing motions blur the consequences of any single gas pulse and stretch the time over which climate responds. Stochastic events punctuate the background. A sequence of large eruptions lifts sulfate aerosols high and cools the planet a few years in a row. A lull returns and greenhouse gases dominate. An impact injects dust that dims a few summers and chills currents into strange paths. Basaltic provinces flood and raise carbon dioxide steadily for centuries. The planet never rests at an exact balance. It hovers along a corridor, shaped by feedbacks that are strongest when conditions stray. If cold advances, weathering slows, carbon dioxide grows, and warmth returns. If heat surges, weathering accelerates, carbon falls, and cool redresses. The corridor is wide enough for lakes to freeze in winter and seas to steam near vents, but narrow enough that the phrase deep ocean persists. The chemistry of the upper air sets a ceiling on greenhouse players. Without oxygen, there is little ozone to intercept ultraviolet, so photolysis is fierce. Methane suffers under that light, but brings along the seeds of haze that can shade the surface if production is great. The altitude of this shading matters. High hazes cool by reflecting sunlight. Low hazes warm by holding heat. The height depends on particle size and vertical mixing, which themselves depend on solar activity and the vigor of convection. The distinction between cooling veil and warming blanket pivots on lengths measured in kilometers and sizes measured in tens of nanometers. In a cold valley at dawn, frost glitters on a plain of volcanic glass. By noon, the frost retreats and leaves a sheen that absorbs sunlight and warms the ground. A breeze rises and curls the air into small eddies that lift dust. The dust glows in the slanting light with a copper tint, then settles when clouds slide over the Sunday, evening gathers, and a soft inversion traps warmth near the surface. Stars harden in the clear air above, while fog thickens in swales. The sequence repeats not as a ritual but as a consequence of balances that stay near the middle. The world remains temperate by never staying still, keeping warmth in motion so that no place hoards either cold or heat for too long. When the faint star brightens on scales longer than lifetimes, the planet bends its cycles to match, drawing down greenhouse gases by faster weathering and by storing carbon in stone. When the star quiets for a spell, the air relaxes its drawdown and allows carbon to accumulate. The thermostat is slow, yet sufficient. Warmth persists because many small guardians stand watch. Gases that return long-wave light, oceans that shuttle heat, rocks that answer to rain and temperature, clouds that switch personalities with altitude, and a rotation that carves the sky into engine belts. The paradox disappears when the tally is honest. Temperate seas under a pale sun are not a miracle. They are the natural outcome of a planet built to exchange. Stone offers instruction through texture. A crystal face is not a blank plane. It carries steps, terraces, and kink sites where atoms sit with bonds unfulfilled. These sites attract molecules from the wandering broth and hold them for a moment longer than the open water would. The pause matters. While held, a carbonyl can swivel to meet an amine. A phosphate can discover a place where charge is balanced just enough to join a sugar. A small acid can shed water and stitch itself to a partner. The surface writes a map of possibilities determined by lattice spacing and dangling charge. Clays speak this language fluently. Montmorillonite swells with water and admits cations into its interlayers. Sodium and calcium nestle there and create a field that organizes monomers by charge and size. When a set of activated nucleotides arrives, their bases lie flat against the silicate sheets, guided by van der Waals attraction and cation bridges. Proximity turns chance into likely. Bonds form that would rarely form in bulk solution, and short strands emerge. When the clay contracts as it dries, the layers press together and drive further links. When it swells again, the strands separate into spaces large enough to admit more monomers. The sheet becomes a patient teacher, cycling between embrace and release. Micas add another skill. Their sheets are stiffer and their interlayers less generous, yet their surfaces are smooth at atomic scales. Peptides lying on a mica face adopt alignments that encourage beta sheets, then rearrange into helices when salts change or temperature shifts. A fabric of ordered chains spreads across a terrace and stabilizes by weak forces that together become strong. As waves pass and recoil, pieces break away and curl into free filaments that carry structure into the water. The memory of the surface persists in the conformation of the strand. Iron sulfide minerals offer electron pathways rather than simple templates. Macinowite and greigite host metallic domains that allow electrons to hop. At their edges, nickel and cobalt occupy positions that resemble lodgings for cofactors. Carbon dioxide bound near these centers accepts electrons and protons in a sequence that yields small carboxylic acids. A thioester forms in a niche where sulfur bridges make departures of water favorable. The mineral behaves like a primitive catalyst with a chassis of rock. Nearby pyrite grows from the same chemistry and opens micropores that vent gradients of pH and potential. A surface and a circuit share the same home. Basaltic glass brings youth and reactivity. Fresh shards fractured by quenching present broken bonds that water rushes to satisfy. The first thin skin that grows over such a shard is a silica gel filled with cations that diffuse slowly. Within that gel, ions arrange into microcompartments separated by gradients invisible to the eye. Organic acids wandering through these networks linger at spots where iron or calcium sits. Condensation reactions make small oligomers that would not survive the open sea. When flow or waves slough the gel, the products release into currents that carry them to the next bench of glass. Zeolites fill space with order that mimics sieve and vessel. Their aluminosilicate frameworks carve channels of precise width and cages of regular size. Ammonium, sodium, and potassium decorate the interior and tune electrostatics. Within these pores, molecules align with the walls and collide in patterns biased by geometry. A two-carbon molecule finds a partner at a corner where the channel narrows. A three-carbon chain bends to pass through and meets a different fate than it would in a broad pond. The rock itself selects. Water outside thinks it is the same water that enters, but within, choices are constrained and outcomes diverge. Evaporite minerals act as mold makers. Halite and gypsum grow as water departs, trapping thin films in inclusions that knit through a crystal like a web of lenses. Within those films, concentrations soar to levels that make unlikely reactions probable. When the crystal dissolves during the next flood, it liberates what it held in a rush that feels like a memory released. On flats where episodic ponds evaporate, polygonal crusts impose geometry on puddles. Each polygon drains differently. Each line concentrates along its rim. The lattice of salt becomes the lattice of reaction zones. Green rust, a layered double hydroxide of iron, toggles between oxidation states with a nimbleness that makes it a useful mediator. Its sheets exchange anions between them and present surfaces that can reduce nitriles or oxidize sulfides, depending on the ambient conditions. In plumes where ferrous iron meets oxygen-free water, green rust forms as a transient. While it lives, it grabs phosphate and carboxylates with equal appetite, then releases them when pH shifts. It plays storehouse and gatekeeper without plan. Molecules visit, stay, and depart in queues organized by charge and size. Silica itself, in the form of opal and gel, provides a gentle touch. Its surfaces are rich in silanol groups that hydrogen bond with alcohols and amines. On a warm bench, these interactions position reactive ends that would otherwise wander apart. When heated a degree or two, the bonds loosen and form new partners a few angstroms away. A shoreline covered in silicious ash becomes an array of weak clamps that hold and release in rhythm with sun and cloud. The clamps are not choosy, but their patience and density allow rare associations to persist long enough to matter. Calcite and aragonite speak with chirality. Their crystal faces present stepped landscapes, where left and right turn are not the same. Enantiomeric molecules see different energies of binding and linger for slightly different times. Over many cycles, a bias develops in the pool adjacent to steps that prefer one hand. A racemic mix on entry departs tilted. The shift is tiny per pass, but a tide that returns daily delivers thousands of passes over years. At a crystal habit that groups terraces into spirals, the path itself selects direction, and the streams of molecules following that path carry the signature into open water. Apatite holds a lesson in reluctant phosphorus. Its lattice takes up phosphate tightly and refuses to yield except under acid or in the presence of competing anions. At fumaroles and hot springs where gases acidify pools, apatite releases a trickle of phosphate that rises sharply as pH swings. In the same basins, reduced phosphorus from metallic visitors can exchange into the lattice and then reappear later in more oxidized forms. The mineral becomes a buffer for a key reagent that otherwise would be either locked away or washed to sea. Along fault gouges where apatite grains grind, fresh surfaces glow with reactivity that fades as they heal. Serpentine and brucite lay foundations for alkaline pores, where peridotite alters in the presence of water. Plates of magnesium hydroxide stack into honeycombs. The walls admit protons differently than hydroxide and set up a persistent gradient from one side to the other. Through these membranes, small acids prefer one path, small bases another. A gradient across a mineral membrane is not life, but it is a push that can be harnessed. Within the semiporous walls, metals embed and create active sites where hydrogen meets carbon dioxide with probability above chance. Pumice rafts extend laboratories across the sea. Their frothy bodies carry interlinked vesicles that stay buoyant for months. Spray washes amphiphiles into those vesicles and leaves behind films that organize and thicken. Sunlight warms the upper skin by day, then the night sea cools it to dew by dawn. The rock acts as a sponge that both shelters and exposes, alternately wet and dry in patches over its surface. A raft travels through thermal zones and deposits chemical cargo where it eventually beaches. What incubated under open sky becomes feedstock for shorelines a continent away. Feldspar breaks into kaolinite and goethite under warm rain. The products coat grains and give them different personalities. Kaolinite presents a white face that reflects and stays cooler under sun. Goethite, a red face that absorbs and warms. Films on these surfaces experience distinct microclimates separated by centimeters. Temperature gently alters reaction rates and shifts equilibria. The nearby presence of both faces makes adjacent pools differ enough that products from one can act as reagents in another when flows mix. The landscape becomes a patchwork of thermal policy controlled by color and mineralogy. Vanadium and molybdenum hide in small amounts in sulfides and oxides. When exposed at surfaces, they change the repertoire of catalysis. Vanadium lowering activation barriers for oxygen transfer, molybdenum assisting in carbonyl activation. Their dispersal is uneven. A ridge rich in vanadium sees oxygenated intermediates that would be scarce elsewhere. A beach with molybdenum-bearing sands yields different carbon chains than a neighbor without. The periodic table intrudes not as a list, but as a mosaic stamped into steep walls and gentle flats. Textures born of stress create galleries for chemistry. Pressure solution etches stylolites along bedding planes and raises serrated seams that focus flow. Microfractures open and close, with thermal expansion each afternoon and wake. In the instant of opening, fresh charge appears at crack tips, attracting ions that coat the edges. In the instant of closing, tiny volumes trap concentrated mixes that react before diffusion can undo the compression. Stone flexes, breathes, and in that breathing teaches molecules to gather, to align, and to depart, transformed. Conductive networks threaded through sediments connect redox couples that would remain isolated in still water. Graphite grains touch pyrite that touches magnetite that touches a splay of smectite. Electrons take the path even where fluids cannot. A reduction that begins where sunlight strikes, a zinc-rich patch ends where sulfides chill in shadow. The connection lets alternating light and dark produce cumulative change rather than reversible stutters. Products accumulate not where they formed, but where the circuit delivers them, at junctions that become hubs of quiet complexity. On a ledge above a tidal notch, an outcrop of mixed minerals faces the sea. Mica flakes make silver plains that mirror the sky. Clay curls into paper-thin scrolls as it dries. Zeolite nodules stud the matrix like seeds set in bread. Halite rims the edge with a filigree of cubes that glitter. Morning mist wets everything. By noon, droplets retreat from hydrophobic patches and collect along hydrophilic stripes. Films thicken and thin according to grain identity. By afternoon, heat drives faint currents along temperature gradients across a span no wider than a hand. By evening, cool air condenses dew that bridges gaps and pulls solutes into new pockets. The day writes an intricate choreography across the rock, without a single living witness. Minerals do not plan. They simply provide landscapes where energy lands and matter lingers. Yet landscape itself is instruction. By holding, aligning, polarizing, and transporting, surfaces narrow the field of outcomes and favor sequences over chaos. In the language of chemistry, that is mentorship. The midwives are mute, but their touch is everywhere that a film of water meets an honest crystal face. Patterns survive because stone insists on pattern. Preference appears because a lattice cannot be any shape at once. Out of those constraints rises order, and from order, the first whispers of function. Two theaters shape chemistry with different stagecraft. In the deep, vents raise mineral towers from black basalt and fill the dark with glimmering plumes. Along sunlit margins, ponds and tide pools breathe in and out with sky and moon, their floors paved in clays and salts. Each offers gradients, each offers shelter and stress. Each trains molecules in distinctive habits that might converge when pieces find one another on journeys no map could predict. At depth, alkaline chimneys grow like organ pipes. Warm fluids seep from peridotite that has met seawater and changed into serpentine and brucite. The seepage carries hydrogen, methane, and carbonate. Walls of carbonate and hydroxide precipitate at the mixing front, leaving behind a foam of micropores separated by thin mineral membranes. Across those walls, pH differs by several units and redox potential by hundreds of millivolts. The pores act as cells before cells exist, with interiors where small acids concentrate and exteriors where seawater holds different ions in reserve. Nickel and iron sit in the walls as catalytic centers, easing transfers of electrons to carbon dioxide and nudging it toward formate, acetate, and small carboxylates that can linger within the labyrinth. A few meters away, hotter black smokers roar. Their jets carry iron, zinc, and copper in sulfide-rich solution. When mixed with cold seawater, these metals precipitate in clouds that dim the water and rim the chimneys with glittering frost. The temperature can exceed limits that fragile intermediates tolerate, yet microcytes within the porous precipitates stay cool enough for chemistry to survive. Sulfide minerals present conductive paths. Gradients pulse as flows surge, but do not vanish. A battery hums quietly in stone, charging and discharging with tides and seismic whispers. At the surface, a different rhythm rules. Pools fill when storms arrive, or tides cross a threshold, then shrink under heat and wind. Salts concentrate, films form on mineral faces, vesicles assemble when fatty acids collect, then grow leaky under high salt, then harden again when rinsed with fresh water. Wet-dry cycles drive condensation reactions that would stall in constant brine. Activated monomers link into short polymers on clay terraces, then peel away when swelled by returning water. Sunlight supplies energy to semiconductors like zinc, sulfide, and titanium oxide, splitting water and exciting electrons that reduce carbon species at mineral defects. Lightning walks across the sky and leaves nitrates and nitrites for the next rain to deliver. In vents, energy comes as gradients across tiny distances. Nanometers separate alkaline interiors from mildly acidic seawater. Protons flow by diffusion, electrons by conduction, creating the possibility of coupling endergonic steps to exergonic ones without dispersing heat into bulk water. In pools, energy comes in packets and schedules. Noon differs from dusk by a spectrum and flux. Dry noon differs from humid dawn in water activity and ionic strength. The schedule itself selects. Replicating polymers that withstand heating and survive drying keep their length better than those that fall apart when the film thins. Membranes that remain intact under salt spikes inherit the chance to encapsulate the day's products. Architecture differs too. Chimney walls enforce microcompartments separated by mineral. Pores connect in networks that allow small molecules to migrate while holding larger ones in place. The structure is three-dimensional scaffolding assembled by precipitation. Shorelines enforce two-dimensional films and layered crusts. Reaction fronts sweep across surfaces as tides retreat. Cracks produce lines of higher concentration where capillary forces draw solutes. Geometry dictates which partners meet and in what order, and geometry here is a tutor that never tires. Phosphorus behaves under these regimens with contrasting moods. In alkaline vents, phosphate adsorbs onto green rust and carbonate walls, then releases in pulses when pH shifts, making brief windows where phosphorylations can proceed. In evaporative ponds, reduced phosphorus from meteorite phosphides reacts into soluble species, then oxidizes toward orthophosphate as days pass. Drying concentrates phosphate enough to form high-energy bonds from simple precursors. Rehydration tests those bonds, and the survivors seed the next cycle. The same element learns to act as energy currency in one theater and as structural joiner in the other. Nitrogen follows its own routes. Deeply, ammonia forms on iron-nickel surfaces when hydrogen is plentiful and bound nitrogen species meet catalytic sites. Ammonia complexes metals and becomes a handle for building heterocycles. At the surface, lightning and ultraviolet carve nitrogen into oxides and cyanides that arrive with rain. Cyanide partners with carbonyls in cold dawns to make alpha-aminonitriles that hydrolyze on warm afternoons into amino acids. The two regimes generate complementary inventories that can mix when runoff carries pond chemistry to the sea or when spray tosses brine onto coastal flats. Membranes face different tests. In alkaline pores, Gradients of pH mean proton accumulation and depletion across micrometers. Fatty acid vesicles that lodge within pores experience proton influx and outflux that alters internal pH. Charged solutes move across thin walls more readily in one direction than the other. Protocells that fortify their membranes with divalent cations or with simple isoprenoid-like lipids hold gradients longer and keep the internal composition slightly apart from the bulk. On shores, osmotic shock rules the day. Vesicles swell under fresh water, shrink under salt, stretch during warming, and relax at night. Those with mixed amphiphiles tolerate stress better than pure fatty acids. Those that trap polymers become more robust because the polymers bind head groups and reduce leakage. Stress acts as selection. Stability earns another sunrise. Information molecules see contrasting challenges. In vents, constant hydration and modest temperatures allow base pairing in small oligonucleotides to persist within pores. Mineral surfaces lined with metals stabilize certain folds and encourage strand elongation by activating 2' or 3' ends in proximity to monomers. In ponds, dehydration favors the formation of phosphodiester bonds and pushes templated copying during the final stages of drying when monomers lie pressed against templates on clay. Rehydration separates strands and allows a new cycle of copying. Error rates differ between regimes. Deep systems favor steady state with lower but continuous extension. Surface systems favor bursts with higher throughput and occasional catastrophic failure. Evolution of chemistry emerges from these rates without any gene in sight. Catalysis adapts. In chimneys, transition metals run the show. Nickel and iron cluster in sulfide matrices that mimic active sites of enzymes that will appear much later. Small cycles reminiscent of acetyl transfers and carbonyl insertions emerge from geochemical constraints. On shores, light energy and minerals dominate. Photoredox cycles on semiconducting grains and organo-mineral complexes with clays and iron oxides give rise to radicals and cationic intermediates that add, subtract, and rearrange carbon frameworks. The outputs differ in flavor. One tends toward reduced organics, compatible with deep anoxia. The other enriches in oxidized intermediates and nitriles produced by atmospheric sparks. Transport links the theaters. Rivers carry nitriles, aldehydes, and salts from land to sea. Storm surge throws marine brines and vesicles back onto flats. Pumice rafts ferry porous laboratories between realms, collecting amphiphiles at the surface and hosting hydrogen-driven reduction in waterlogged interiors. Spray aerosols pack brine and organic films into droplets that ride wines along coasts, landing as invisible dew on mineral faces meters above the high tide line. No boundary is absolute. Exchange ensures that neither regime operates as a closed box. Time sorts winners and temporary successes. In the deep, reactions that couple to persistent gradients accumulate products laid down as films on mineral walls. These films alter conductivity and serve as new platforms for further chemistry. On land, reactions that exploit cycles of extremes produce polymers and membranes that weather repetition. Hybrids emerge when pond-borne vesicles enter vents and discover proton gradients that can drive internal reactions, or when vent-borne organics wash ashore and encounter dehydrating glossaries that favor linkage. The idea of a single origin turns soft in this view. Intersections matter more than borders. Observation at human scale can sketch a day that reveals both classrooms. Morning light slants across a salt flat studded with clay terraces. Thin films spread, glimmer, and begin to dry. Vesicles twitch at the edge of a receding puddle, gathering solutes as their skins tighten. Midday bakes the surface. Polymers extend on clays where activated monomers lie like alphabet tiles pressed into pages. A squall arrives, hammers the ground, and sweeps the products toward a channel that leads to the sea. In the afternoon, the channel joins a bay whose floor slopes toward a ridge of chimneys. Warm alkaline water rises in a shimmer. Within the mineral foam, small acids accumulate and bind to nickel sites. The evening tide turns. Some vesicles lodge in pores and feel a gentle push of protons. Others drift out and return to the shoreline in a final surge. Night cools the flats. Dew restores hydration without rinsing everything away. Stars move. The cycle awaits dawn. Each lab has flaws. Deep systems risk dilution without membranes that maintain compartments. Surface systems risk destruction when extremes exceed tolerance, yet flaws are teachers. Chemistry learns to protect itself by aggregating into films, by adopting membranes, by binding to minerals, by coupling endergonic to exergonic steps. It learns to harvest light when light is offered, and to exploit gradients when gradients are present. It learns redundancy by running in parallel across landscapes. Selection operates on assemblies and cycles, not on genes. Persistence is the criterion. Anything that lasts interacts with something else that lasts, and networks take form from those interactions. A quiet synthesis waits at the confluence. Imagine a vesicle formed on a warm flat, loaded with a handful of short polymers and a few energy-rich bonds born of dehydration. Carried by a stream into a sheltered vent, it meets a wall that leaks protons and finds that its interior chemistry can steal that gradient to push an unfavorable reaction forward. Imagine a filament of reduced carbon grown in a chimney pore, torn free by a surge and tossed onto a clay terrace where drying stitches it into a more complex chain. The laboratories trade students, the curriculum expands, the phrase origin ceases to mean a point. It becomes a braid, one strand of cycles in darkness and pressure, one strand of cycles in light and air, and the place where they cross again and again. On a shoreline at dusk, the sea glows faintly over distant chimneys. In the foreground, a cracked crust of salts outlines hexagons as fine as a turtle shell. A breeze lifts mist from the surf and spreads it like a veil over the flats. Under that veil, films shift, vesicles gather, and minerals quietly polarize their surfaces for the night. Offshore, micropores pulse with hydrogen and carbonate, and walls carry electrons one lattice site at a time. No voice announces preference. The planet allows both. In their debate, chemistry finds not contradiction but vocabulary, and from vocabulary the first grammar of persistence. Instruction begins as an accident that refuses to fade. A strand forms on a mineral terrace, not long, not clever, just enough to fold on itself and hold by hydrogen bonds that zipper along paired edges. In that fold lies specificity. Bases choose partners by shape and charge, not by preference but by constraint, and the constraint writes a pattern that can be read by monomers drifting through the film. When the water thins and ions crowd the surface, reactive ends lie close to their complements. A bond forms, then another, and a copy grows beside its guide like a shadow laid in polymer. The copy is not perfect. Perfection would halt invention. Enough matches emerge that the figure of the original survives, and enough mismatches occur that the figure of tomorrow can differ. Templates meet limits quickly. Too much water, and the strands wander apart. Too little and chemistry stalls in glass. Cycles reconcile the conflict. Drying compresses monomers against a model. Re-wetting separates parent and child, and invites a second round. Heat loosens stubborn knots. Cool pauses reactions before they overrun the canvas. Only a few sequences endure the schedule. Those that fold too tightly refuse to open for copying. Those that flop remain unstructured and collect useless partners. Those that hold just enough secondary shape become both readable and stable. Selection acts without a jury. A strand that survives the cycle is present for the next one. A strand that fails disappears into tars and harmless fragments. Backbones compete for simplicity and strength. Phosphodiester bonds offer both a sturdy spine and a chemistry that can be made under cycles of dehydration and rehydration when activated monomers are present. On clays, these links arise with modest encouragement. On mineral sulfides, other couplings appear that later give way to the same phosphate, chiming once conditions allow. Side groups tune everything. Bases that stack smoothly predispose strands to align on their own. Bases that bind too eagerly choke copying by sticking in knots. Mixtures sort themselves as cycles continue. The catalogue of workable monomers narrows towards sets that can pair, stack, and take a charge from the environment. Catalysis awakens within the strand itself. Loops and hairpins bend the polymer into three-dimensional forms that present pockets where metals lodge and where small molecules can rest in precise poses. A fold that originally stabilized a template now presses reactive groups together and lowers a barrier. A bond forms not between monomer and template, but between two free molecules guided by the fold. Activity is faint at first. A million loops may catalyze a handful of reactions in a day, yet the loop that helps a neighbor to lengthen will be found beside that neighbor more often than chance predicts. The neighborhood changes as a consequence. Copies of helpful folds remain near each other longer. The landscape of function appears from the geography of proximity. Peptides join the practice by arriving as short chains born from cycled pools of amino acids and nitriles. Some are random, many are inert. A few present side chains that bind metals and arrange water into cages. When such a peptide clings to a strand, it stabilizes a fold and extends a lifetime under heat or salt, or it accelerates a local reaction by positioning a substrate. In return, the strand that benefits is copied more often or survives longer. Cooperation does not require promise or plan. It requires only that two parts raise each other's odds of persistence. A peptide that enhances a fold wins not by making itself, but by making its partner better at making partners. Membranes refine the stage. Vesicles assembled from fatty acids and alcohols already swell and divide with tides. When strands slip inside these compartments, the interior becomes a small world with altered concentrations and buffered pH. Charged monomers cross the walls more slowly than neutral ones, so chemistry within differs from chemistry without. A strand that can help its own vesicle absorb building blocks gains an edge. A fold that weakens at just the right time makes the membrane more permeable during inflow and then tightens when danger passes. The membrane learns to host by simply selecting contents that favor its endurance. Energy enters the loop as a molecule rather than a field. High-energy bonds formed by condensation on hot stone travel into compartments as tiny coins. Thioesters and phosphoanhydrides transfer their energy to steps that need a push. Inside a vesicle lodged near a gradient of pH, protons cross the wall in one direction more readily than the other. A fold in the membrane that carries a mineral cofactor allows electrons to creep along a path that couples the proton flow to a redox reaction. No machinery stands recognizable yet. There is only a coincidence of structure and opportunity that allows an unfavorable linkage to occur a little more often inside than outside. That little more often accumulates, and accumulation is the first arithmetic of survival. Errors write variation into the archive. Copying fails at certain motifs, succeeds at others, and the distribution of mistakes differs with temperature, salt, and mineral neighbors. Too much error and information evaporates into noise. Too little and exploration stops. A sweet spot appears where descendants resemble ancestors closely, but carry enough difference to test a changed condition. Hypercycles emerge when one strand's product enhances another strand's copying, and a third returns the favor to the first. These loops do not need central control. They need local increase in probability where partners meet and act. If the loop sits within a compartment that keeps partners together, it persists against dilution. If a loop disperses, it dissolves into the average chemistry of its surroundings. Length tempts but punishes. Longer strands hold more instruction and fold into richer forms. They also break more easily and copy more slowly. Shorter strands survive shocks and copy swiftly but offer fewer tricks. A compromise arises. Hairpins and motifs recur that fold assistance into small packages. Repeats appear that allow a damaged region to be repaired by templating against an intact neighbor. Eventually, tiled assemblies of short motifs outperform single heroic polymers. Modularity becomes a virtue long before any protein scaffold exists to exploit it. Chirality firms its hold as copying relies on match and stack. Mixed-handed monomers fit poorly in duplexes. Strands that happen to be enriched in one-hand template more efficiently than racemic cousins. Mineral faces that offered subtle preference earlier now drive the system toward near homochirality as cycles reinforce small biases. Membranes that incorporate uniform-handedness pack more tightly and leak less. the same tilt that aids copying aids containment. The environment chooses by physics. The result looks like intention only because the winning geometry repeats. Competition arrives in the simplest terms. Protocells draw from the same pool of monomers and energy carriers. Those that uptake faster or degrade slower increase in number by division. Division is not precise. Contents partition by flow and chance. Strands that tend to stick to inner walls distribute unevenly. A daughter may inherit a combination of catalysts that differs from its sibling. Some lineages bloom for a few cycles, then fade when the ambient mix changes. Others adapt by presenting more permeable membranes in times of scarcity and tighter skins in times of plenty. Phenotype here is the sum of chemistry and membrane physics expressed as survival during a week of storms, and Sunday, communication begins as leakage. Vesicles exchange lipids through brief contacts, strands slip out with amphiphile clusters and find refuge in neighbors. Peptides adsorb to outer surfaces and act beyond their compartment. Signals do not yet exist, but influence does. A protocell rich in a particular catalyst alters the local medium enough that others nearby benefit or suffer. Clusters of compartments co-evolve traits of permeability and content simply by lasting in a shared condition. Geography organizes function as surely as sequence does. A threshold approaches when a strand folds into a form that helps copy its own kind more than it helps a random neighbor. Ribozyme-like behavior in which a loop aligns monomers along a template raises the rate of faithful extension. Now, inheritance moves from mere presence to active assistance. A compartment containing such a strand is more likely to produce daughters with similar strands. The feedback tightens. Information begins to point to itself and is not merely copied because it happened to be nearby. Direction is born from a bias in kinetics, not from desire. Another threshold appears when a fold assists the synthesis of amphiphiles that strengthen the host membrane. Now content helps container, and container returns the favor by protecting content. A line is crossed between passive residency and mutual reinforcement. Such partnerships seed lineages that can weather harsh cycles more reliably than others. They do not think, they do not plan, they persist, and persistence is the simplest definition of success when chemistry competes. Evening gathers over a beach of damp clay. Vesicles wobble as a thin sheet of water slides back toward the sea. Some split along lines of weakness and reseal as smaller spheres. A few carry inside them short strands curled into productive folds and a handful of energy-rich bonds that survive the day. Offshore, gentle turbulence drifts these globes toward a calmer eddy. Overnight, the membrane tightens in the cool and becomes less leaky. Inside, strands that can catalyze a step or two act in the dark. Their rates low, but not zero. Dawn will bring another bake, another round of intake, another test of strength and compatibility. Out of countless failures and brief successes, a few patterns will endure long enough to compile a fragile script. No narrator announces the moment when copying becomes heredity rather than repetition. The difference is not a single leap, but an accumulation of small preferences that together form a ratchet, a fold that helps another fold to exist. A membrane that preserves a contents biased toward doing useful work, an energy currency that closes a cycle and prevents reversal. When these elements overlap within a compartment, the system can outlast storms that would erase a simple chain left in the open. It is still chemistry, but it is chemistry with memory. The first scripts are written in soft fonts and edited by tide, light, and stone. They are not yet words, but they already speak. Stones cannot speak, so instruments translate. A beam of ions knocks atoms from a crystal face and counts daughters against parents, turning decay into time. U to PB clocks tell when a grain cooled below a threshold. Lu to HIF ratios sketch the separation between mantle and crust. Sman to Nard balances trace a lineage of melts and residues. Dates and ancestries accumulate until a terrain gains a biography precise enough to anchor speculation. The precision arrives from physics that never tires. The story arrives from patterns that emerge when hundreds of grains say nearly the same thing in slightly different dialects. Isotopes remember weather no eye has seen. Oxygen in a zircon holds a signature that betrays contact with water at low temperature. Hydrogen in serpentine whispers of a source reservoir richer or poorer in heavy atoms. Sulfur in ancient sediments carries mass-independent fractionation, a pattern that can be born only under skies with little oxygen and abundant ultraviolet. Chromium in banded iron hints at redox landscapes written by volcanoes and light rather than by enzymes. These fractionations are not just numbers, they are shadows thrown by absent actors, silhouettes of atmospheres and oceans inferred from the way atoms prefer one route over another when light is hard or when acids fall. Fluid inclusions trap ancient breaths. A halite crystal grown from a shrinking lake inherits tiny cavities of brine. A quartz vein, born from hydrothermal circulation, locks away bubbles of gas and thin sheets of fluid. Under a microscope, inclusions gloss like planets under glass. Heating stages coax bubbles to expand and contract, and from their behavior, pressures and compositions can be inferred. Raman spectroscopy lights the cage and reads the line fingerprints of sulfate, methane, or carbon dioxide trapped for eons. These miniature archives anchor dynamic models that would drift without a fixed point. Magnetism offers a second kind of fossil. As igneous rock cools, iron minerals align with the prevailing field and freeze direction and intensity into their lattices. The strength of that frozen signal says how stout the ancient magnetosphere was, and by extension how well the planet deflected solar wind. Single crystal paleo-intensity methods pluck the faintest echoes from tiny grains, reheating them under controlled fields until they confess the field they once felt. A shield strong enough to matter implies an atmosphere able to stand and oceans not stripped by storms of particles. The argument is circumstantial, but the chain is tight enough to hold attention. Heat budgets can be measured indirectly. Neutrinos born from radioactive decay pass through the planet as if it were glass, but a few glance-off detectors sunk into quiet rock. Their flux narrows the range of radiogenic heating inside the mantle and crust. That heat has paced convection, volcanism, and hydrothermal vigor. It has governed how quickly the surface cooled, how quickly continents thickened, and how energetically metamorphic fluids coursed through deep pathways. Even a soft constraint on heat refines every model that asks how fast water cycled and how often magma rose. Simulations reach where outcrops cannot. General circulation models reconstruct winds, storms, and temperatures on worlds with slower sunshine, denser carbon dioxide, and near ozone-free skies. Photochemical models compute how ultraviolet splits gases, how radicals recombine, and where hazes grow. Ocean models track gyres on a globe with fewer continents. Geochemical box models balance carbon between air, sea, and stone when no tree breathes and no shell falls. Each run is a controlled fantasy, bound by conservation laws and by the handful of numbers rock provides. Ensembles of runs become probability fields. Patterns that persist across many assumptions gain credibility. Patterns that require fine-tuning invite skepticism. Laboratories compress time with energy. A discharge chamber sparks through a mixture of gases and yields nitriles, aldehydes, and amino acids that rain onto glass. A shock tube drives an impact like pressure wave through a cloud of dust and gas, then quenches the result into tar or rings, depending on recipe. A laser ablates a mineral in solution and paints the fluid with metal ions that catalyze carbon fixation down pathways unavailable in the open. A cold finger grows ice veins that concentrate solutes. A heated stage dries films to crusts that crack into polygons where chemistry intensifies along edges. Repeatability matters more than spectacle. Blanks run beside experiments to catch contamination. Controls check that outcomes track inputs. Microfluidic devices turn cycles into algorithms, channels narrower than a hair move, droplets through zones of heat and chill, salt and fresh, light and shade. Vesicles inflate and deflate on schedule as pressure pulses. Strands meet activated monomers against a clay-coated wall, then are peeled and shunted to a cooler pocket where they fold. Valves inject bursts of phosphate or cyanide or iron to mimic storms or vents. Because volumes are tiny, rare events leave footprints large enough to measure. Because geometry is fixed, Outcomes can be mapped against constraints and not just reported as marvels. Analytical chemistry reads whispers as if they shouted. High-resolution mass spectrometers distinguish isobars by parts per million, orbitraps, cradle ions, and listen to their motion, converting frequency into mass with eerie fidelity. Chromatography separates families indistinguishable by eye. Synchrotron beamlines focus ultraviolet spectra matched to early skies and let minerals and films feel the same colors that once fell from a faint star through a hazy air. Scanning probes trace atoms on a mica terrace and watch a peptide arrange into a line because the surface asked politely. Atom probe tomography plucks atoms one by one from a zircon and rebuilds clusters in 3 dimensions, confirming that radiogenic lead never wandered far from where it was born. Some tests require the planet itself. Hydrothermal fields on the mid-ocean ridge cut through peridotite and show serpentinization writing hydrogen into water vented as buoyant plumes. Alkaline edifices in the deep Atlantic rise as chimneys and exhale warm carbonate-laced fluids into darkness, offering natural versions of geochemical batteries assembled in reactors. Volcanic lakes in high deserts load the air with chlorine and fluorine and challenge membranes with acid. Evaporitic basins crust and crack on a seasonal pulse strong enough to measure. Field geochemistry follows gradients across meters and seasons rather than centimeters and hours, and those scales matter when translating from glassware to globe. Meteorites deliver mannequins of ancient chemistry. Carbonaceous stones fall under curated skies and are rushed into clean rooms where gloves touch only once and powders are weighed on balances that live in filtered air. Spectra map amino acids, sugars, and phosphorus compounds in mixtures that mirror synthesis in ice and irradiation in deep time. Heating experiments separate primordial signals from contamination. Minerals within meteoritic matrices, like schreibersite and forsterite, are ground and added to water to test whether their reduced phosphorus and metal surfaces replay the same tricks in the lab. The results do not prove settings, but they constrain what is feasible for chemistry to attempt. Planets near and far act as controls. Mars preserves crust older than most terrestrial surfaces and displays minerals formed by water under atmospheres with little oxygen. Titan packages aerosols into a global experiment in nitriles. Enceladus and Europa offer plumes laced with salts and organics vented from dark oceans. Comets carry ices that remember molecular clouds. Measurements from these worlds stretch expectations. If a pathway works anywhere under familiar physics, it asks to be considered here with appropriate context. If it fails everywhere except a narrow niche, it remains a candidate but loses generality. Uncertainty is a feature, not a flaw. Rocks have been recycled, oceans have erased, impacts have reset landscapes. What survives is partial and biased toward minerals that resist. To honor that bias, statisticians build Bayesian frameworks that treat each result as a likelihood, not a verdict. Priors reflect physics and chemistry known from first principles. Posteriors reflect what remains plausible after data. The approach does not create facts. It quantifies humility and prevents one spectacular measurement from dictating an entire world. Trade-offs haunt reconstructions. A dense early atmosphere warms but also scatters ultraviolet needed for certain steps. Strong hazes shield fragile products but steal photons from photocatalysts. High salinity accelerates some condensations yet tears vesicles. Investigators answer by mapping phase diagrams of possibility. Axes become nitrogen, carbon dioxide, methane, salt, and photon flux. Regions within maps host pathways that can overlap into networks. The network approach replaces single origin points with neighborhoods of chemistry that cross-feed. Tests seek intersections where a single set of conditions supports several key steps simultaneously. Timing is not guessed, but inferred. Day length alters tide period and weather patterns. Lunar recession can be modeled backward using present tidal dissipation and geological hints of ancient cycles preserved in rhythmites and layered deposits. Even if the oldest records lack clear tidal marks, models bracket plausible day lengths and tidal amplitudes, feeding into calculations of wet-dry pacing along coasts and energy in mixing. Solar output at given epochs is constrained by stellar evolution, not by whim. With those boundaries in place, climate models explore corridors of temperature that align with isotopic evidence for liquid water rather than with personal preference. Negative results matter. A membrane that fails under magnesium levels implied by mantle rocks eliminates certain lipid families as primary actors. A polymerization that requires concentrations of phosphate incompatible with measured mineral solubilities undercuts a favored route. A paleo intensity too low to protect the upper air eliminates photochemical schemes that demand delicate windows of ultraviolet. Publishing these closures is as important as celebrating successes. Every narrowing increases the density of truth in the remaining space. Contamination haunts every bench. Every glove, every vial, every puff of breath carries modern signals strong enough to drown the faint voices of old chemistry. Clean labs enforce airflows and blanks and isotopic labels that reveal intrusions. Field blanks travel to deserts and vents and return unopened to become controls. Chain of custody follows rocks from fall to freezer. The discipline looks paranoid because the stakes demand it. The most exciting peak in a spectrum means little if it could have ridden in on dust from a sleeve. Interpretations resist single ownership. Geochemists read isotopes as a climate diary. Planetary scientists weigh orbital dynamics before admitting a gas budget. Organic chemists test whether a proposed pathway survives side reactions when all plausible partners share the flask. Modelers prod each other's code and compare outputs under standardized boundary conditions. The community behaves as a self-correcting organism, blind in places, yet alert where it counts. Disagreement sharpens tools. Consensus, when it arrives, feels earned rather than comfortable. Even with instruments capable of counting atoms and models that march across decades of CPU time, some questions remain sketches. How quickly gradients can be captured by compartments depends on microgeometry, few rocks preserve. How red the haze was depends on particle sizes seldom frozen in stone. How often impacts reset local chemistry depends on a flux punctuated in ways only partially recorded by craters. Patience becomes a method. New quarries open, new detectors quiet themselves under mountains, new missions bring back dust from an asteroid's tender surface. A table in a quiet lab holds an array of tiny vials. Some are cloudy from a week under ultraviolet, matched to a pale star. Some are clear, run through a cycle of drying and dew. One shows a hint of iridescence where vesicles packed against a glass wall. Nearby, a rock slice glitters under a probe that counts lead atoms and reconstructs a clock older than almost anything else. On a monitor, a climate model resolves belts of cloud on a planet with more carbon dioxide and a shorter day. The scene lacks drama to anyone seeking thunder, yet this is how a world without witnesses is given back its mornings. Each instrument trims a guess. Each experiment reveals a corner case. Each model holds variables constant long enough to see cause separate from coincidence. Testing the unremembered requires inventions that do not care if the answer pleases. The only demand is coherence. Silence carries weight when everything else is motion. A planet turns under a sky without voices, yet the quiet is not emptiness. It is grammar without nouns, a cadence set by tides, winds, and the slow folding of stone. Night leans into day, and day leans back into night, and the seam between them holds 1,000 small transitions that no mind collects. Water thins over rock and leaves lacework salt. Vapor cools into dew and then escapes to sky. Heat rises, not as a shout, but as a constant hum. In this hush, patience becomes the only currency, and the world pays itself in time. Meaning begins as recurrence. A tide climbs to the same notch on a black wall and draws back in the same curve. A storm returns to a thermal boundary and builds towers that flatten at the same height. A vent breathes warm fluid at a steady beat set by invisible pressures far below. Repetition writes memory into terrain and sea without a single glyph scratched into stone. Coves deepen, flats widen, terraces lengthen, not because they intend to, but because force meets material with the same strength every time. This is what a world without listeners looks like when it learns to keep rhythm. The absence of witnesses does not erase beauty. Metal-rich waters throw green shadows across a bay. Basaltic domes shine like wet onyx at dawn. Ice on a high plateau fractures into plates, thin as bark, and slides with a soft chime that no ear collects. Halos ring the moon in the still air of winter. Sundogs hang at equal angles, where crystals turn light into geometry. If the word sublime can be stripped of human need, it fits here. The scene does not ask to be admired, it is sufficient to itself, an alignment of path and law that repeats for as long as materials allow. Gravity provides a theme that never ends. Mountains grow and are shaved, basins sink and are filled, waves respect fetch and depth and draw lines in sand that parallel the shore within a margin set by grain size. Snow packs into fern and then into crystalline stone that flows around obstacles as if it were thick honey. Even lava, the most theatrical of rocks, keeps to curves set by slope and viscosity. What looks like chaos from a distance reveals structure to anyone patient enough to watch longer than a season. The hush reveals order by removing the distraction of narrative. Distance folds into intimacy at small scales. A film thickens around a grain and holds a world inside that the ocean cannot see. A pore connects to another pore and creates a corridor for drift that would take centuries in open water and seconds in stone. Dew beads on a crystal face and magnifies the terrace steps beneath, turning atoms into hills and valleys for a moment. Heat from the interior rises through floors and warms a patch of ground large enough for a hand, then vanishes into air a meter above. The planet is vast, but it expresses itself locally, through touches so small that even a future eye would need help to see them. Silence permits speculation about luck without insisting on a verdict. A small change in rotation would have softened tides and rewritten shorelines. A thinner crust would have cracked into different maps. A magnetic field a little weaker would have let storms from the star strip gases more quickly. The numbers fell as they did, not because a gambler chose them, but because a set of initial conditions walked forward and refused all other options. Contingency is not favor. It is inertia applied to conditions. The quiet makes this clear. There is no applause, only continuation. In such a world, possibility is the loudest word. Chemical networks assemble, fail, and assemble again. Gradients sharpen, blur, and sharpen again. Assemblies cross thresholds, then fall back, then cross again with different partners. Nothing holds power over time except cycles that couple to cycles. The sea breathes with the sky. The crust breathes with the mantle. The air breathes with light. These breaths are not metaphors. They are counts of exchange, and if numbers can be called alive without offense, then the arithmetic here is already lively. There is comfort in the thought that quiet comes first. Noise is a later invention. Sound requires ears, and meaning requires minds. Before either appears, the world rehearses structures that minds will one day learn to name. Fracture, convection, diffusion, condensation, radiance, refraction, fatigue, annealing, eutectic, resonance, drift. A lexicon is waiting long before a speaker arrives. When a speaker does arrive, the terms will seem like inventions. They are recognitions of an older language spoken by rock and water to each other since the beginning of weather. Equilibrium and disequilibrium share a border that moves like a tide line. On one side, balance holds and grace appears as structure that persists. On the other side, imbalance drives and grace appears as change that refuses to rest. The border migrates over minutes and over millennia. A glacier advances into a valley and then retreats, leaving drumlins that point like hands. A shoreline sags under sediments and then rebounds when currents shift. A plume rises and then fades, leaving a plateau that invites rain. Stability is not stasis. It is a posture held under pressure and altered by any new weight. Silence is not a synonym for peace. Lightning fractures clouds and shakes stone. Impacts tear holes and set oceans sloshing in sheets that scale cliffs. Fumaroles cough acid that etches glass and turns slopes white with salts. Rivers eat banks with teeth hard enough to carry boulders. Winds throw sand against rock until both complain. Yet even in violence, no intention intrudes. Destruction here is merely reorganization. Heat returns to air, mass returns to slopes, ions return to solution. The ledger remains balanced and the entries are elegant in their own severe script. If memory can exist without a subject, then it exists here as record in crystals, as layered residues in chemical sediments, as pale scars of strand lines that mark out paleoclimate on amphitheater walls. Time writes redundantly. A single story appears in zircons under a mountain, in clays on a plain, in glass under a desert crust, in flows frozen deep under sea. Redundancy is not waste. It is the only protection against accident in a universe that does not promise archives. Silence instructs in redundancy by requiring that messages be written in many hands. There is humility in understanding that nothing needs to happen next. If no cell arises, the planet continues to exchange heat and mass until its star grows too bright. Then its oceans steam, then its crust softens, then its iron relaxes. There is tragedy in that thought only when a mind is around to grieve. In the hush, there is only the physics of long decline. That this decline does not unfold is not proof of favour or teleology. It is simply the branch that was taken among many that could be listed if a ledger existed large enough to hold them all. When thought finally appears, it will step into an inheritance already immense. The mind will think it has arrived to a blank stage. It will not understand at first that the set is already built, the lights already hung, the orchestra already deep into a slow movement, the themes introduced long ago. It will take centuries for the mind to hear the bass line in the tide, the counterpoint in the mantle, the syncopation in weather. Then it will name them and pretend that naming creates them, and later it will learn to smile at its own arrogance. The planet at dawn before senses and stories is an altar without gods, a cathedral built by thermodynamics and erosion, a wilderness whose paths are curves of least action. It stands under a sky made of chemistry and light, sits upon a foundation made of heat and pressure, wears garments made of water and stone. In its quiet, one hears the most honest hymn any world can sing, a song that says only this: I exchange, I endure, I equilibrate, I drift, I surprise, I return. The lyric has no chorus. It does not need one. The melody is looped by cycles that never end. A morning opens over a plain of wet basalt. The first light scatters on mist. The sea lifts and sets its shoulder against the shore. In a shallow pool a film breaks and seals, with the delicacy of a breath. Far out, a plume sends a grey feather into the wind. High above, the moon writes a pale path across the sky. No witness stands, yet everything is already an audience to everything else. The planet listens to itself by responding, and in those responses a story accumulates that no voice has to tell. Quiet is not the absence of speech. Quiet is the first speech, and the world pronounces it perfectly. Night drapes the water with a velvet patience, and stone holds its heat like an ember cupped in both hands. A thin cloud crosses the face of the moon and leaves a brushstroke so faint that even the sea hesitates to reflect it. Far below, vents whisper through mineral throats, and bubbles rise like rosaries counting prayers no mouth has formed. Along the shore, a sheet of dew joins grains of salt into rings and ladders, a crystal alphabet that will collapse at dawn and reassemble by noon. There is no witness to certify the beauty, and beauty requires none. The planet keeps time with its own pulse, a metronome hidden in tides, storms, and the long exhalations of rock. In this hush, possibility lies everywhere, not as promise but as structure. Charged faces lean towards soluble hands, gradients coil into springs that push without sound, films thicken into membranes that tremble at the touch of light. The star lifts, not yet fierce, and pours a pale arithmetic across waves. Each photon tabulates a choice, reflection or absorption, warmth or return, a sum that always balances even as patterns shift. The arithmetic becomes music when repeated, and repetition becomes place. From such measures, a future enters quietly, not as a prophecy fulfilled, but as a threshold crossed, because cycles have taught chemistry how to last. When thought finally arrives and gives names to pools and winds and stones, it will hear an older naming already underway. Rain has been naming slopes with rivers. Freeze has been naming fissures with wedges of ice. Heat has been naming minerals with veins and halos. The mind will add syllables to the chorus and find itself answered by echoes older than language. Then it will learn humility with joy. The first word spoken under that sky will not begin the story. It will simply join it, a late stanza added to a hymn that began in silence and never needed applause. End of script. Sweet dreams.